Hello there, and welcome to Science for Sleep, where curiosity slows its pace and science takes the long way around. Tonight's gentle exploration turns its attention outward, far beyond familiar skies, toward a question that has quietly followed humanity since we first noticed that the stars were not just lights, but places. Is interstellar travel actually impossible? Not difficult, not inconvenient, not something for a distant future, but fundamentally, stubbornly, unreachably impossible. It is a heavy question, but we will handle it lightly, with patience, without rushing toward an answer that does not want to be rushed. When people imagine travelling to the stars, the images are often neat and confident. A sleek ship, a bright engine, a calm crew waking from sleep as a distant sun fills the window. The idea feels almost reasonable, especially after decades of science fiction, diagrams, documentaries, and optimistic headlines. And yet, when scientists actually sit down and do the math, when they begin replacing imagination with numbers, something curious happens. The dream does not shatter all at once. Instead, it slows, it stretches, it becomes heavy, like trying to walk through water that deepens with every step. Before we drift too far into the science, take a quiet moment. Where are you listening from right now? A bedroom, a sofa, a train seat, maybe somewhere between wakefulness and sleep. And what time is it there, in your small local pocket of the universe? Somewhere on Earth, night has already settled. Somewhere else, it is just beginning. And overhead, regardless of the hour, the stars are there, keeping their distance as they always have. If you find this kind of exploration calming or quietly intriguing, you can like the video or subscribe. It helps this slow, thoughtful corner of science reach others who may need something gentle to listen to as the day winds down. And now, without urgency, without conclusions yet, let us ease into the story of distance, physics, and the uncomfortable possibility that the universe may be far less travel-friendly than our stories suggest. When we talk about interstellar travel, we're not talking about going to the moon or even Mars. Those journeys, while difficult, belong to a completely different category. They're trips across a cosmic front yard. Interstellar travel means leaving the solar system entirely. It means crossing the empty space between stars. And that space, it turns out, is not just empty. It is enormous in a way that resists intuition. The nearest star system to our own, Alpha Centauri, is a little over 4 light-years away. That sounds manageable until the words are unpacked. A light-year is not a measure of time, but of distance. It is how far light travels in 1 year, moving at the fastest speed the universe allows. That distance is about 9.46 trillion kilometers. Multiply that by 4, and the numbers already begin to slip past the edge of everyday meaning. Writing them down does not help much. Saying them aloud helps even less. The human brain evolved to navigate forests, rivers, and plains, not trillions of kilometers of vacuum. To make the scale more tangible, imagine shrinking the solar system down so that the Earth is the size of a grain of sand. The Sun would be about the size of a large beach ball, roughly 10 meters away. Neptune, the outermost planet, would orbit about 300 meters from the Sun. Even at this scale, the nearest star would not be on the same beach. It would be hundreds of kilometers away. And between those 2 points, there would be almost nothing. That nothingness is part of the problem. In space, there are no roads, no refueling stations, no air, no natural braking system. Once you leave Earth, everything you need must come with you or be generated along the way. Every gram matters. Every bit of energy must be accounted for. And the farther you want to go, the more the costs begin to rise not linearly but brutally. It is tempting to assume that the main barrier is speed. If only we could go faster, the reasoning goes, the stars would feel closer, and speed is certainly a challenge, but it is not the first one. Even reaching a small fraction of the speed of light requires staggering amounts of energy. The fastest spacecraft humans have ever built, probes like Voyager 1, are travelling at about 17 kilometers per second. At that pace, reaching Alpha Centauri would take over 70,000 years. That is not a journey. That is a geological era. You might imagine simply building a faster engine, a bigger rocket, a more efficient fuel. But rockets face a fundamental limitation known as the rocket equation. The faster you want to go, the more fuel you need. But the more fuel you add, the heavier the spacecraft becomes, which means you need even more fuel to move that fuel. It becomes a compounding problem, one that grows more severe the closer you try to get to interstellar speeds. Even advanced concepts like nuclear propulsion, fusion drives, or antimatter engines, while theoretically capable of much higher performance, still run into this wall. The energy required is not just large, it is comparable to the total energy output of entire civilizations, and unlike science fiction engines, real propulsion systems must obey conservation laws. They must push against something. In the emptiness between stars, there is very little to push against. Then there is time. Even if a spacecraft could reach a significant fraction of light speed, the journey would still take years or decades as measured from Earth. A crew would age, systems would degrade, tiny errors would accumulate, and all the while, the destination star would not be waiting politely. It would be moving, orbiting the galaxy at hundreds of kilometers per second, just like our own sun. Navigation becomes a problem measured not in kilometers, but in patience and precision stretched over lifetimes. Some point out that relativity offers a strange comfort. At very high speeds, time passes more slowly for the traveller than for those left behind. A crew travelling near light speed could, in principle, reach distant stars within a single lifetime, at least from their own perspective. But this does not make the journey easier, it makes it lonelier. Everyone they left behind would age rapidly in comparison. Civilizations would change, languages would shift. Return would mean arriving in a future that no longer remembers the departure, and this assumes the spacecraft survives at all. Interstellar space is not completely empty. It contains gas, dust, radiation, and high-energy particles. At everyday speeds, these pose little threat. At near light speed, even a grain of dust becomes a bullet with catastrophic energy. Shielding against this requires mass. More mass means more fuel. And so, the loop tightens again. There is also the question of reliability. No machine humans have ever built is designed to operate flawlessly for centuries. Electronics degrade, materials fatigue, software fails. Even with redundancy, the odds of something going wrong approach certainty as time stretches on. A mission measured in decades is already pushing the limits of what engineering can reasonably promise. A mission measured in centuries becomes less like travel and more like an experiment in whether anything can last that long. It is here that the word impossible begins to whisper, not shout, just whisper, because each problem alone seems solvable in theory. Better engines, smarter shielding, longer lifespans, but taken together, they form a mesh of constraints that tighten as you move outward. Distance multiplies energy demands. Energy demands increase mass. Mass complicates propulsion. Time magnifies risk. Risk erodes feasibility. Still, humans are persistent. When faced with barriers, we do not usually stop at the first wall. We look for workarounds. We imagine alternatives. We ask whether the problem itself is framed correctly, and so the question shifts slightly. Perhaps interstellar travel is not impossible in principle, but impossible in the way crossing an ocean with a spoon is impossible. The laws of physics do not forbid it, but they do not make it welcoming either. At this point, it is useful to notice something subtle. The universe does not seem designed for easy movement between stars. On planetary scales, motion is manageable. Within solar systems, gravity provides pathways, but between stars the gaps are vast and unstructured. No natural highways, no gentle gradients, just long stretches of cold, dark inertia. It is almost as if the universe encourages local complexity but discourages wandering. This observation has led some scientists to wonder whether interstellar travel is not just technologically difficult, but evolutionarily unlikely. Civilizations may arise, develop science, explore their own systems, and then plateau. Not because they fail, but because the cost of going farther outweighs the benefit. Staying home becomes the rational choice, and yet the idea refuses to fully settle. Humans continue to send probes outward. We continue to listen for signals. We continue to imagine ships crossing the void. The question remains open, hovering somewhere between physics and philosophy. Is interstellar travel actually impossible, or is it simply beyond the kind of creatures we are, bound by bodies, time, and finite resources? As these thoughts drift, there is no need to decide anything yet. The stars are patient. They have been waiting long before humans ask questions about them, and they will continue waiting long after. For now, it is enough to sit with the scale of the problem, to feel how the universe stretches wider than intention, and to notice how even asking the question changes how we see our place within it. When people say space is big, they're usually understating the problem without realizing it. Big is a word we use for rooms, cities, maybe oceans. Space is not big in that sense. It is excessive. It is stretched far beyond the point where ordinary comparison remains useful. And when scientists talk about the difficulty of interstellar travel, this is often the part they hesitate over, not because it is complicated, but because it is almost embarrassing how bad the numbers are. The difficulty is not hidden in advanced equations or exotic physics. It sits right at the surface, in basic arithmetic that anyone can do, which makes it harder to escape. You do not need a doctorate to see the issue. You only need a calculator, a sense of scale, and the patience to keep multiplying until the result stops feeling meaningful. Let's begin gently, with something familiar. Earth orbits the Sun at a distance of about 150 million kilometers. That sounds enormous, but we cross it constantly with light, heat, and radio signals. Spacecraft traveling to Mars deal with distances of tens to hundreds of millions of kilometers, depending on orbital alignment. These journeys are difficult, expensive, and slow, but they are not alien. They fit just barely into human planning horizons. Months, sometimes years, still within a working lifetime. Now move outward to the edge of the solar system. Neptune orbits about 4.5 billion kilometers from the Sun. Even at that scale, sunlight still reaches it in a few hours. Spacecraft like Voyager took more than a decade to get there, moving faster than any crewed vehicle ever built. Already the timescales are stretching. Mission teams retire. Engineers who designed the instruments are no longer available when data arrives. And yet, in astronomical terms, this entire solar system is still a tiny bubble. If the Sun were reduced to the size of a marble, the orbit of Neptune would fit inside a small room. The nearest star would still be several kilometers away. That gap, that empty separation, is the vastness problem in its purest form. The distance to Alpha Centauri is about 4.37 light years. Light travels roughly 300,000 kilometers per second. That is fast enough to circle Earth more than 7 times in a single second. Even at that speed, crossing the gap between stars takes years. Nothing with mass can reach or exceed that speed. Everything slower stretches the journey further. If a spacecraft travelled at 10% of light speed, which is far beyond anything humans have ever built, the trip would still take over 40 years from Earth's perspective. That is 40 years of continuous operation, 40 years of shielding, navigation, power generation, thermal control, and structural integrity. 40 years without a single unrecoverable failure. And that is only to the nearest star. At 1% of light speed, the journey stretches to over 400 years. At the speeds we can actually achieve today, it becomes tens of thousands of years. These are not durations that fit easily into any existing human system. Governments do not plan that far. Companies do not survive that long. Cultures change completely over much shorter spans. This is where the vastness problem becomes less about technology and more about alignment between scales. Human civilization operates on years, decades, occasionally centuries. interstellar distances demand millennia even under optimistic assumptions. There is a mismatch that no engineering breakthrough automatically resolves. It is tempting to imagine that faster propulsion alone could bridge this gap. If only we could go faster, the argument goes, the universe would feel smaller. But speed improvements do not compress distance linearly in any helpful way. Doubling your speed halves your travel time, yes, but when the starting number is 40,000 years, halving it does not suddenly make it practical. It only makes it slightly less absurd. There is also a subtle psychological trick at work. When distances are too large to visualize, the mind quietly disengages. 4 light-years sounds only 4 times larger than 1 light-year, but 1 light-year is already so far beyond everyday experience that multiplying it does not add emotional weight. The numbers lose their ability to alarm. Scientists, however, cannot afford that luxury. When designing missions, they must account for every kilometre. Navigation errors that are negligible within a solar system become catastrophic over interstellar distances. A deviation of a fraction of a degree can mean missing an entire star system by billions of kilometres after decades of travel. There is no margin for casual correction. You cannot pull over and adjust. Communication adds another layer. Even at light speed, messages between Earth and a nearby star take years to arrive. A spacecraft encountering a problem cannot ask for help and wait for instructions in any meaningful sense. It must be entirely autonomous. Every decision must be anticipated decades in advance. Every failure mode must be handled by systems that cannot be updated in real time. Then there is targeting. Stars are not stationary points. They orbit the centre of the galaxy at enormous speeds. Over the course of a long journey, the destination star moves significantly. Navigation must account not just for where the star is now, but where it will be when the spacecraft arrives, decades or centuries later. This is not impossible in principle, but it compounds uncertainty. Even more unsettling is the realization that most of the distance is spent not near anything interesting, but in deep interstellar space. For years at a time, nothing changes. No planets, no landmarks, just a sparse scattering of atoms and the occasional high-energy particle. Systems must function in isolation, without external reference points, without repair, without rest. The vastness problem also affects energy storage. Any propulsion system capable of sustaining high speeds for long durations must either carry enormous energy reserves or generate energy continuously. Both options face physical limits. Fuel adds mass. Reactors require shielding. Energy conversion produces waste heat that must be radiated away, which becomes harder as power increases. As distances grow, the inefficiencies accumulate. Tiny losses matter. Slight inefficiencies in power systems, minuscule leaks, microscopic material degradation all become mission-ending over long enough timescales. On Earth, maintenance handles these issues. In interstellar space, there is no maintenance, only design. This is why even uncrewed interstellar probes remain hypothetical. While concepts exist, they often rely on extreme assumptions. Ultralight sails pushed by powerful lasers, self-healing materials that do not yet exist, power sources that remain stable for centuries, navigation systems that never drift. Each assumption might be plausible on its own. Together they form a chain where the weakest link decides the outcome. The vastness problem also interacts with economics. Interstellar missions would require enormous upfront investment for returns that may not arrive within any reasonable institutional time frame. Scientific data might come back after the careers of everyone involved have ended. Political support would need to persist across generations. This is not a technical obstacle, but it is a real one. Some suggest bypassing the issue by sending information instead of matter. Probes could transmit data without returning. This helps slightly, but it does not reduce travel time. The probe still has to cross the same distances. The information still arrives decades later, and the probe still must survive the journey. Others propose sending self-replicating machines that can use local materials to build copies of themselves, spreading slowly through the galaxy. While intriguing, this idea assumes a level of autonomy, reliability, and resource utilization that remains speculative. It also introduces ethical and control concerns that complicate the picture further. At this point, it becomes clear why people avoid doing the full calculation. The math does not inspire optimism. It does not yield neat timelines or heroic milestones. It yields spreadsheets full of long durations, large energy requirements, and cascading constraints. The universe does not say no outright. It simply makes every step expensive. And yet, the vastness problem is not just an obstacle. It is also information. It tells us something about the structure of the universe and our place within it. The stars are visible to us but not easily reachable. Information travels freely, but matter does not. Local systems are rich and complex, while interstellar space is sparse and indifferent. This arrangement may not be accidental. On cosmic scales, stars form, burn, and die without ever interacting directly. Planetary systems evolve largely in isolation. Life, if it arises, must make do with its immediate neighbourhood. The universe seems to favour pockets of activity separated by long silences. Understanding this changes how we frame the question. Instead of asking why we have not yet travelled between stars, we might ask whether the universe ever intended such travel to be common. Perhaps interstellar journeys are not the next step after spaceflight, but a fundamentally different category of endeavour, one that lies outside the normal trajectory of technological progress. None of this proves impossibility. Physics rarely closes doors completely, but it does suggest that interstellar travel is not merely an extension of what we already do. It is not just more rocket or better engine. It requires confronting scale itself, accepting that the universe operates on dimensions that dwarf biological intuition. It is tempting to think of speed as a simple thing. Faster means sooner, slower means later. On Earth, this intuition works well enough. A faster train reaches the station first. A quicker route saves time, but once the conversation leaves the ground and drifts into the structure of the universe itself, speed stops behaving like a friendly variable and starts acting more like a boundary. Not a suggestion, not a technical challenge to be overcome with clever design, but a rule that appears to be woven into reality itself. The speed of light is often introduced casually, almost playfully, as if it were just another impressive number. Light moves at about 300,000 kilometers per second in a vacuum. That sounds fast, and it is. But the deeper significance is not that light is quick. It is that nothing with mass can ever move faster than it. No engine, no particle, no clever workaround has ever violated this limit. And after more than a century of testing, physicists are increasingly confident that this is not a temporary restriction waiting for a loophole. It is a structural feature of the universe. This realization did not arrive gently. Before the 20th century, time and space were treated as separate, stable backdrops against which motion played out. Speed was relative in the everyday sense. If you were standing still and someone ran past you, they were moving and you were not. If you were both on a train, the numbers changed, but the idea remained straightforward. There was no universal speed that everything had to agree on. Then experiments involving light began to behave strangely. No matter how fast an observer moved, light always appeared to travel at the same speed. Whether you chased a beam or ran away from it, it never slowed down or sped up relative to you. This was deeply uncomfortable for classical physics. It forced a choice. Either measurements were wrong, or the concepts of time and space themselves needed a revision. The revision won. Time and space were no longer independent. They became aspects of a single structure called space-time. Speed, particularly the speed of light, became more than a measurement. It became a conversion factor between space and time, fixing how much of one could be exchanged for the other. This has consequences that feel almost rude in their refusal to accommodate intuition. As an object accelerates toward the speed of light, its energy requirement increases dramatically, not gradually but asymptotically. Each additional fraction of that speed demands more energy than the last. Reaching light speed would require infinite energy. Infinite is not a figure of speech here, it is a mathematical statement. No finite process can get you there. This means that even in principle, a spacecraft cannot be accelerated to the speed of light, let alone beyond it. You can approach it, you can get closer and closer, but you will never arrive. The universe does not allow mass to make that final step. At first glance, this seems like a problem mainly for science fiction writers. After all, most proposals for interstellar travel do not require light speed. They only need a respectable fraction of it. 10%, 20%, perhaps half. But the speed limit still dominates the conversation, because even approaching it carries serious costs. Energy is the first. To accelerate even a modestly sized spacecraft to a significant fraction of light speed would require energy on a scale that rivals the output of entire planets, and that energy must come from somewhere. It must be stored, generated, or delivered over time. Each option carries mass, complexity, and risk. Then there is time dilation. As speed increases, time slows down for the moving object relative to those left behind. This is not a trick of perception. It is a measurable effect. Clocks on fast-moving spacecraft tick more slowly than clocks on Earth. Biological processes slow accordingly. Aging itself becomes relative. This is sometimes presented as a benefit. A crew travelling at high speed could cross great distances within a single lifetime, at least from their own point of view, but this framing hides a deeper issue. Time dilation does not reduce the energy cost of the journey. It does not reduce the wear on the ship. It does not make navigation easier. It simply rearranges who experiences the waiting. For those left behind, the wait becomes longer. A mission that feels like decades to the crew may span centuries on Earth. Communication becomes not just delayed, but effectively severed. Responses arrive after generations have passed. Decisions made by the crew cannot be informed by events at home. They become temporal islands, disconnected not by distance alone, but by time itself. There is also the matter of momentum. At relativistic speeds, even tiny particles encountered along the way carry enormous energy relative to the spacecraft. A single atom of hydrogen, which would be harmless at lower speeds, becomes a high-energy projectile. Collisions that would normally be trivial become destructive. Shielding against this requires mass. Mass requires energy to accelerate. The loop closes again. The speed limit also interacts with navigation in subtle ways. At high velocities, the universe appears distorted. Light from ahead becomes compressed into a narrower field of view. Radiation intensity increases in the direction of travel. Instruments must operate in an environment that no spacecraft has ever experienced for extended periods. Designing systems to function reliably under these conditions is not a solved problem. One might wonder whether the speed of light is merely a limitation of current physics, destined to be overturned by a deeper theory. After all, scientific revolutions have happened before, but this particular limit has proven stubborn. It is not a single equation or assumption that enforces it. It appears across multiple independent frameworks. Relativity, quantum field theory, and causality itself all lean on this boundary. If information could travel faster than light, cause and effect would become ambiguous. Events could influence their own pasts. The sequence of actions would lose coherence. The universe would struggle to maintain a consistent narrative. The speed limit, it seems, is not just about motion. It is about preserving order. This makes the idea of simply going faster feel less like a technological challenge and more like a request to renegotiate the rules of reality. And reality so far has not shown much interest in renegotiation. There are, of course, proposals that attempt to sidestep the limit rather than break it. Concepts like warp drives and wormholes do not involve moving through space faster than light, but reshaping space itself. In these ideas, space contracts in front of a vessel and expands behind it. allowing effective superluminal travel without locally exceeding the speed limit. On paper, the equations allow such configurations, but they come with requirements that are, to put it gently, extreme. Negative energy densities, exotic matter with properties never observed, stability conditions that may not be physically realizable. These are not small engineering hurdles. They are questions about whether the necessary ingredients exist at all. Even if such structures could exist, they raise additional concerns. Creating and controlling space-time distortions would require precision on scales that dwarf any current technology. Any failure could be catastrophic. And again, none of this addresses the energy cost. Moving space-time itself is not cheaper than moving through it. There is also an often overlooked aspect of the speed limit that affects exploration even at lower velocities. Signals, not just ships, are constrained. You cannot see what is happening somewhere else until light from that event reaches you. The universe is always shown to us as it was, not as it is now. The farther away something is, the older the information we receive. This means that even discovering habitable worlds around distant stars involves a built-in delay. By the time a signal reaches us, the conditions we are observing may no longer exist. A planet that appears promising might have changed dramatically in the meantime. Interstellar exploration is always slightly out of sync with reality. As these layers accumulate, the speed limit begins to feel less like a single obstacle and more like a web. It constrains motion, communication, causality, energy, and perception simultaneously. You cannot address one aspect without encountering the others, and yet, the universe does allow something remarkable. While matter is slow and constrained, information encoded in light moves freely at the maximum speed. We can observe stars across the galaxy. We can measure their composition, their motion, their age. We can map regions we will never visit. In this sense, the universe is generous. It allows knowledge to travel even when bodies cannot. This raises an uncomfortable possibility. Perhaps interstellar travel was never meant to be physical in the way we imagine. Perhaps the intended mode of connection between stars is observation rather than visitation, understanding rather than presence. That idea does not sit well with a species that evolved by moving, exploring, and expanding. Humans crossed oceans long before they understood their full size. We colonized continents without knowing what lay beyond the horizon. Movement is deeply tied to progress in our history. But oceans and continents existed on a planet that did not enforce an absolute speed limit. Ships could always, in principle, go faster. Winds could be stronger, hulls could be sturdier. There was no asymptote waiting to stop them. The universe is different. It allows approach, but not arrival. It permits ambition, but not disregard. The closer you get to its limits, the more it pushes back, not with explosions or barriers, but with rising costs and slowing returns. This does not mean interstellar travel is forbidden. It means it is constrained in a way that reshapes the problem fundamentally. It is not about building a faster engine. It is about deciding whether the trade-offs make sense at all. At first glance, rockets seem like the obvious bottleneck. When people imagine interstellar travel failing, they picture engines that are not powerful enough, fuel tanks that run dry too quickly, or propulsion systems that simply cannot push hard enough against the emptiness of space. The intuition is understandable. Rockets are loud, dramatic, and visibly limited. They shake, burn, separate, and fall away. It feels natural to assume that if we could just build better ones, everything else would fall into place. But when scientists look closely at the problem, rockets turn out to be something of a distraction. Not because propulsion does not matter, but because it is not where the deepest constraints live. Even a perfect rocket, one with flawless efficiency and unlimited reliability, would still be trapped by other limits that have nothing to do with thrust or flame. To understand why, it helps to strip rockets down to their most basic role. A rocket is not really an engine in the usual sense. It is a momentum exchange device. It throws mass backward in order to move forward. That backward thrown mass carries momentum, and conservation laws ensure the spacecraft gains an equal and opposite amount. This principle works anywhere, even in the vacuum of space, and it is why rockets are so versatile. But that same principle also creates the core difficulty. Every bit of speed you gain must be paid for by expelling mass. The faster you want to go, the more mass you must throw away, and the faster you must throw it. This is not a flaw of chemical rockets in particular. It applies to all reaction-based propulsion, whether chemical, nuclear, or hypothetical fusion systems. This relationship is captured in the rocket equation, which is deceptively simple and deeply unforgiving. It links the change in velocity a spacecraft can achieve to the exhaust velocity of its propellant and the ratio between its initial and final mass. What the equation reveals, once you sit with it long enough, is that gains in speed require exponential increases in fuel mass. That word, exponential, is the quiet villain here. It means that doubling your desired speed does not require double the fuel. It requires vastly more. Add a little more speed, and the fuel mass balloons. Add a little more still, and the spacecraft becomes mostly fuel, with the actual payload shrinking into a rounding error. This is why even advanced propulsion concepts struggle. Nuclear thermal rockets can eject propellant faster than chemical ones. Fusion engines, if they ever become practical, could do better still. But none of them escape the exponential curve. They only shift it slightly. The fundamental shape remains. Suppose you design an ideal rocket that can operate perfectly for decades, never failing, never leaking, never degrading. Even then, to reach relativistic speeds, the amount of propellant required would dwarf the mass of the ship itself. The ship would become a fuel container with a tiny capsule attached. And that fuel must be accelerated too, which means even more fuel to move the fuel that moves the ship. At this point, it becomes clear that rockets are not failing because they are poorly engineered. They are failing because they are doing exactly what physics allows and no more. The limitation is not technological immaturity, it is structural. This realization often leads to a moment of disappointment. If better rockets are not the answer, what is? But before jumping ahead, there is another subtlety worth noticing. Rockets only matter during certain phases of a journey. They accelerate at the beginning, they decelerate at the end. For most of the trip, especially in interstellar space, the spacecraft simply coasts. Once a ship reaches its cruising speed, rockets become almost irrelevant. The ship will continue moving at that speed without further propulsion. Space offers no friction to slow it down. From that perspective, propulsion seems like a one-time hurdle rather than a continuous burden. And yet, that initial hurdle is everything. The cost of reaching cruising speed dominates the entire mission. The energy invested at launch determines how fast you go, how long the journey takes, and how much shielding you need. Propulsion choices cascade into every other design decision. Still, even if propulsion were somehow solved perfectly, other issues would remain untouched. Rockets do nothing to address distance. They do nothing to reduce communication delays. They do nothing to mitigate time dilation or radiation exposure. They do nothing to guarantee system reliability over centuries. This is why focusing too heavily on rockets can be misleading. It encourages the belief that interstellar travel is mainly an engineering challenge, waiting for a breakthrough engine. In reality, propulsion is just one piece in a tightly coupled system of constraints. Consider energy. Rockets require energy to operate, but energy itself must be generated, stored, or delivered. Chemical energy is dense by everyday standards, but laughably weak compared to what interstellar travel demands. Nuclear energy offers improvements, but introduces radiation, shielding, and political complications. Antimatter would be extraordinarily efficient, but producing and storing it safely remains far beyond current capability. Even if energy generation were no longer a problem, energy dissipation would be. High-power systems produce heat. In space, heat can only be removed by radiation. Radiators must be large. Large radiators add mass and present targets for damage. Again, propulsion improvements ripple outward into other vulnerabilities. Then there is the issue of precision. Rockets are blunt instruments at interstellar scales. Tiny variations in thrust, imperceptible during short missions, can lead to enormous deviations over decades. Course corrections would be required, which means additional fuel, additional complexity, and additional risk. Navigation itself becomes less forgiving. Within a solar system, gravitational landmarks help. Planets, moons, and the sun provide reference points. In deep interstellar space, there is almost nothing to orient by. Stars are distant. Parallax shifts are tiny. Instruments must maintain accuracy over long periods without recalibration. Rockets also do nothing to address human factors. A faster engine does not solve psychological strain, social stability, or biological limitations. It does not protect against bone loss, muscle atrophy, or long-term radiation damage. It does not guarantee that a crew will remain functional, cooperative, or even alive across generations. This leads to an uncomfortable conclusion. Rockets feel like the main issue because they are visible and dramatic, but they are not where the hardest problems hide. They are the most obvious obstacle, not the most decisive one. To see this more clearly, imagine a thought experiment. Suppose tomorrow someone invents a propulsion system that can accelerate a spacecraft to 10% of the speed of light with ease. It is safe, reliable, and energy efficient. Rockets, in their traditional form, are no longer a concern. What changes? Travel time to the nearest stars drops to a few decades. That is an improvement, but not a transformation. Missions still span lifetimes. Communication delays remain. Radiation hazards intensify. Shielding becomes more critical. Targeting precision becomes more demanding. Return trips become impractical. The existence of a better engine helps, but it does not unlock a wave of routine interstellar travel. The universe remains large. Time remains stubborn. Risk remains cumulative. This suggests that the true barriers are not located in any single component. They emerge from the interaction between scale, time, and fragility. Rockets are merely the first place where those interactions become visible. There is also a historical bias at work. Human technological progress has often been driven by better engines. Steam engines enabled railways. Internal combustion engines enabled cars and planes. Jet engines shrank the planet. It is natural to assume that another propulsion leap will do the same for the stars, but each of those transitions occurred within environments that did not fundamentally resist motion. Airplanes could always, in principle, go faster. Ships could always, in principle, carry more fuel. There was no absolute boundary waiting to stop them. Space introduces such boundaries. The speed limit is one, energy density is another, human lifespan is a third, reliability over centuries is a fourth. Rockets intersect with these limits, but they do not define them. This is why many modern interstellar concepts move away from traditional rockets altogether. They explore light sails pushed by lasers, not because rockets are weak, but because pushing from afar avoids carrying fuel. Even then, the challenges remain severe. Laser arrays must be enormous. Alignment must be perfect. Deceleration at the destination becomes its own problem. Other proposals imagine magnetic sails interacting with interstellar plasma or harvesting momentum from stellar winds. These ideas are clever, but they operate at the margins. They shave difficulty rather than eliminate it. Seen this way, rockets are not the villain of the story. They are the messenger. They reveal how expensive speed really is. They make visible the cost of pushing matter through a universe that is not designed for easy transport. This reframing changes how the question is approached. Instead of asking how to build a better rocket, the deeper question becomes whether physical travel is the right goal at all. Perhaps interstellar exploration, if it happens, will not look like ships crossing space, but like instruments extending perception, or information being exchanged in ways we do not yet fully understand. For now, though, the focus remains on understanding the problem clearly rather than escaping it prematurely. Rockets, dramatic as they are, turn out to be a relatively shallow layer. Peel them back and the true difficulty is still there, waiting patiently. Distance sounds neutral when you say it quickly. It feels like a measurement, something passive, something that can be crossed if you have enough patience or a powerful enough tool. But when distance stretches beyond all practical frames of reference, it stops behaving like a neutral quantity and starts acting like a force. Not a force in the physical sense, but a persistent pressure that shapes what is possible and what quietly fades into theory. Between stars, distance is not just large, it is dominating. It dictates timelines, erodes reliability, magnifies uncertainty, and turns otherwise manageable problems into compounding ones. It is not dramatic in the way explosions are dramatic. It does not announce itself with noise or light. It simply sits there, unmoving, indifferent and vast, enforcing its terms without negotiation. Within a solar system, distance is something engineers can work around. Travel to the moon takes days, travel to Mars takes months. These spans are long enough to be inconvenient but short enough to remain psychologically and logistically coherent. Mission control can plan, crews can be trained and replaced, budgets can be justified, mistakes can sometimes be corrected. Between stars, all of that breaks down. The tyranny of interstellar distance begins with time, but not in the abstract sense. It begins with the simple reality that anything which takes decades or centuries to complete cannot rely on continuity. People change, institutions collapse, technologies become obsolete, even languages drift. A mission designed today may arrive in a future that no longer shares its assumptions, priorities, or even its point of origin. This is not speculation. Human history provides plenty of examples. 200 years ago, there were no electric grids, no computers, no satellites. Political borders were different. Scientific paradigms were incomplete. Cultural norms were unrecognizable by modern standards. Expecting a multi-century project to remain coherent across such changes is not just optimistic, it is structurally unrealistic. Distance forces time to stretch, and stretched time dissolves continuity. This affects every layer of an interstellar mission. Consider design. Spacecraft systems would need to operate for durations longer than any machine humans have ever relied on without maintenance. Even the most durable infrastructure on Earth requires constant upkeep. Bridges are inspected, power plants are serviced, software is updated. Without intervention, systems decay. In interstellar space, there is no intervention. There is only what was built at launch. Materials degrade under radiation. Mechanical components wear, even in vacuum. Electronics suffer from bit flips and cumulative damage. Lubricants break down, seals weaken. Every physical system trends toward failure given enough time. Engineers can slow this process, but they cannot stop it. Distance ensures that time will be long enough for these processes to matter. Redundancy is often suggested as a solution. Build multiple systems, duplicate critical components, add backups for the backups. But redundancy increases mass. Mass increases energy requirements. Energy requirements complicate propulsion. The trade-offs cascade. And redundancy does not solve every problem. If a design flaw exists, it exists in all copies. If a long-term environmental factor was underestimated, it affects every redundant system equally. Distance gives small oversights decades to mature into mission-ending failures. Navigation also bends under distance. Within a solar system, gravitational landmarks provide orientation. Trajectories can be corrected using planetary flybys or solar reference points. Between stars, there is nothing comparable. Navigation relies on distant stars whose apparent positions change slowly and subtly. Instruments must maintain extreme precision without recalibration for decades. Even slight drift becomes catastrophic over interstellar spans. A tiny angular error at launch can translate into missing an entire star system by astronomical distances. Course corrections require fuel. Fuel is finite. Every correction eats into margins that were already thin. Distance also erodes feedback. On Earth or in near-Earth space, problems can be diagnosed and addressed through communication. Engineers observe data, identify anomalies, and send corrective commands. Between stars, communication delays stretch into years. A spacecraft encountering trouble cannot wait for instructions. It must solve problems autonomously or fail silently. This demands artificial intelligence systems capable of handling unforeseen situations reliably for decades. Not narrow task automation, but broad decision-making under uncertainty. Such systems do not currently exist, and building them introduces ethical and safety concerns of its own. Then there is the issue of arrival. Distance does not end when the destination is reached. Slowing down is as difficult as speeding up. A spacecraft arriving at a star system at high velocity must shed enormous kinetic energy to avoid simply passing through and continuing onward. Deceleration requires fuel, interaction with stellar environments, or pre-positioned infrastructure. None of these are trivial. If deceleration fails, the journey becomes a flyby, not a visit. Data collection windows shrink. Opportunities vanish in hours or days after decades of travel. Distance compresses reward into narrow time slices. Distance also imposes asymmetry. The farther a mission goes, the less meaningful return becomes. Even if data is transmitted back successfully, it arrives long after it could influence the mission itself. Knowledge flows one way, control does not. For crewed missions, distance becomes more than an engineering constraint. It becomes a psychological one. Humans are not well adapted to living with irreversible separation. Knowing that Earth is not just far away, but unreachable within a lifetime, changes how risk is perceived. Decisions become heavier, mistakes become existential. Isolation on Earth is buffered by the possibility of return. Even the most remote environments still exist within a shared planetary context. Interstellar distance removes that safety net entirely. Home becomes a historical concept rather than a physical place. Some propose generation ships as a way around this. Instead of sending individuals, send populations. Let entire communities live and die aboard a vessel that becomes a moving world. In theory, this bypasses individual lifespan limits. In practice, it introduces new layers of complexity. A generation ship must sustain not just bodies, but cultures. It must maintain social stability, education, governance, and purpose across centuries without external reference. It must prevent drift into dysfunction. It must adapt to unforeseen challenges while preserving core mission goals. Distance ensures that no external correction is possible. Whatever happens aboard that ship happens alone. History shows that societies change rapidly even under stable conditions. Values shift, power structures evolve, conflicts arise. Expecting a closed system to remain aligned with its original purpose over many generations is an extraordinary assumption. Distance also affects motivation. Why continue a mission whose payoff will be realized by distant descendants rather than those making sacrifices today? Altruism exists, but it is not infinite. Over time, goals may be reinterpreted, delayed, or abandoned altogether. Even uncrewed missions face a similar issue in abstract form. Data collection priorities defined at launch may no longer be relevant upon arrival. Scientific questions evolve, instruments become outdated, discoveries made elsewhere may render the mission less meaningful before it completes. Distance locks decisions in place while knowledge moves on. There is also the simple matter of opportunity cost. Resources devoted to interstellar travel are resources not devoted elsewhere. On timescales of centuries, entire civilizations could rise and fall using those same resources to solve local problems, explore their own systems, or pursue entirely different paths. Distance stretches not just journeys, but trade-offs. It is important to notice that this tyranny is not dramatic. There is no single moment where distance announces victory. Instead, it slowly grinds down feasibility by amplifying every weakness. Time magnifies fragility. Isolation magnifies uncertainty. Separation magnifies risk. This is why interstellar distance feels qualitatively different from terrestrial or even interplanetary distance. It does not merely require more of the same effort, it changes the nature of effort itself. The universe seems arranged to allow local exploration but discourage wandering too far. Planetary systems are rich enough to occupy attention for millennia. Asteroids, moons and planets offer resources, challenges and variety. From a survival perspective, spreading within a star system already provides resilience. Leaving that system requires confronting distance on its own terms, without shortcuts. And yet distance does not make interstellar travel logically impossible. It makes it practically hostile. It imposes costs that scale faster than benefits. It forces every assumption to justify itself over timescales that resist planning. This distinction matters. Impossible implies a hard stop. A law violated, a door closed. Distance does not close the door. It simply makes the room beyond so far away that reaching it consumes nearly everything else. Time is one of those ideas that feels solid until you press on it. In daily life, it behaves reliably enough. Minutes follow minutes. Days accumulate into years. Cause comes before effect. You wake up. Things happen. You go to sleep. This consistency is so familiar that it feels fundamental, like gravity or air. It does not usually occur to us that time itself might behave differently under different conditions, let alone that it might offer any form of comfort in a discussion about interstellar travel. And yet, when distance and speed begin to dominate the conversation, time quietly changes its role. It stops being just a background measure and starts becoming an active participant. Not an obstacle exactly, but not a saviour either. Something stranger. Something that eases one burden while worsening another, offering relief that comes with a cost attached. This is where relativity enters the picture, not as an abstract theory or a set of equations, but as a practical consequence of trying to move very fast across very large distances. The core idea behind time dilation is simple to state and difficult to absorb. Time does not pass at the same rate for everyone. The faster you move relative to something else, the slower your time passes compared to it. This is not a matter of perception or psychology. It is a physical effect, measured repeatedly, predicted accurately, and built into modern technology. At low speeds, like those we experience on Earth, the effect is so small it can be ignored. Driving on a highway does not noticeably slow your aging. Flying in an airplane barely makes a difference. But as speeds increase and approach the universe's speed limit, the effect becomes dramatic. For an object moving very close to the speed of light, time slows down significantly relative to a stationary observer. A clock aboard a fast-moving spacecraft ticks more slowly than a clock left behind on Earth. Biological processes slow in the same way. Heartbeats, cell division, aging itself all follow the slowed clock. This leads to an initially appealing idea. If time slows down for travellers, then long journeys might not feel long to them. A trip that takes decades or centuries from Earth's perspective might only take years or even months from the traveller's point of view. In principle, this means that interstellar journeys could be survivable within a single human lifetime, at least for those aboard the ship. This is the strange comfort of relativity. Distance stretches time unbearably for observers at rest, but speed compresses it for those in motion. On paper, this looks like a partial solution to the tyranny of distance. You cannot make the stars closer, but you can make the journey feel shorter by moving fast enough. The math is clear. At sufficiently high speeds, the time experienced by the traveller shrinks dramatically. But this comfort is unevenly distributed. While time slows for the crew, it speeds up comparatively for everyone else. A ship that experiences 10 years of travel might return to find that a century has passed on Earth. Friends are gone, cultures have changed, languages may sound unfamiliar, political systems may no longer exist. Even if communication was maintained during the journey, every message would have arrived years late, reflecting a past that no longer aligns with the present. Relativity does not eliminate separation. It transforms it. This creates a deeper symmetry in interstellar travel. From the inside, the journey might feel manageable. From the outside, it becomes a historical event unfolding across generations. The travelers become time migrants, moving not just through space, but into the future of their origin world. This has profound implications for motivation, planning, and meaning. A mission designed to explore another star system may succeed scientifically, but it cannot realistically expect reintegration. Return becomes symbolic rather than practical. The travelers do not come home. They arrive somewhere else in time. This is often glossed over in optimistic discussions of relativistic travel. The focus stays on the subjective experience of the crew because that is where the comfort lies. But comfort for one group can mean disconnection for another. Relativity does not shorten the journey for the civilization that launched it. It also does nothing to reduce the engineering burden. Time dilation does not make the ship age more slowly in terms of wear and tear relative to its own frame. Components still operate for the same number of onboard years. Radiation exposure still accumulates relative to the ship's clock. Structural fatigue still progresses according to the time experienced on board. In other words, relativity reduces the biological burden on travelers, but not the mechanical one. A ship traveling at high speed still has to function flawlessly, for however long the journey takes in its own frame. If that is 10 years, then 10 years of perfect operation is required. If it is 50, then 50. Time dilation does not magically compress engineering requirements. It simply shifts who experiences the waiting. There is also the matter of energy. To achieve significant time dilation, speeds must be extremely high. Approaching even half the speed of light requires enormous energy. Approaching 90% requires far more. As velocity increases, the energy cost rises steeply. Time dilation becomes cheaper only in terms of lived experience, not in terms of physics. This introduces a trade-off. To gain comfort in time, you must pay in energy, mass, and complexity. The more you rely on relativity to make journeys tolerable, the more extreme your propulsion system must be. And as discussed earlier, propulsion systems do not scale kindly. Another subtle issue arises from acceleration itself. Time dilation is not just about speed, but about changes in speed. A ship must accelerate to its cruising velocity and eventually decelerate. These phases introduce forces that affect both crew and structure. Sustaining comfortable acceleration over long periods requires careful design. High acceleration shortens the time to reach cruising speed but increases stress. Low acceleration reduces stress but lengthens the journey's initial phase. Neither option is free. Then there is the psychological aspect. While time dilation reduces subjective duration, it does not eliminate awareness of separation. A crew knows that the outside universe is aging rapidly relative to them. Every moment they experience corresponds to many moments elsewhere. This knowledge changes the meaning of choice and consequence. Decisions made aboard the ship ripple forward into a future the crew will never fully understand. There is no shared present with the people they left behind. They live in different temporal contexts, connected only by delayed signals. This can create a sense of detachment that is difficult to predict. It may foster focus and commitment, or it may erode motivation. Humans evolved in environments where cause and effect were closely linked in time. Relativity stretches that link thin. Communication delays compound this effect. Messages sent from Earth arrive at the ship years later. Replies take just as long to return. Conversations are no longer dialogues. They become exchanges of recorded history. Advice arrives too late to matter. Support becomes symbolic. Even within the crew, relativity introduces complexity. If different parts of a mission involve different velocities or gravitational environments, time may pass at slightly different rates for different individuals. These differences are usually small, but over long durations they can accumulate. Coordinating systems and experiences across varying timeframes requires careful synchronization. On Earth, we already account for tiny relativistic effects in satellite systems. GPS satellites experience time differently due to both speed and gravity. Without corrections, navigation errors would accumulate rapidly. In interstellar contexts, these effects become more pronounced and more difficult to manage. Relativity also challenges our intuitions about simultaneity. Events that appear simultaneous in one frame of reference may not be simultaneous in another. This is not just a philosophical curiosity. It affects coordination. It affects causality chains. It affects how events are ordered and interpreted. For a ship travelling at relativistic speed, what counts as now becomes frame-dependent. The concept of a shared present between the ship and Earth dissolves. There is no universal moment they both agree on. Planning must account for this, adding another layer of abstraction to already complex missions. Despite all this, relativity remains one of the few aspects of physics that seems to offer something positive in the interstellar context. It does not solve the problem, but it softens one edge of it. It allows individual travellers to survive journeys that would otherwise be biologically impossible. It offers a way to trade time for energy. This trade, however, is not neutral. It favours those who leave over those who stay. It privileges the traveller's experience at the expense of continuity. It makes interstellar travel less about exploration and more about transition into a future that no longer shares your past. In this sense, relativity reframes interstellar travel as a one-way process. Not necessarily physically one-way, but culturally and temporally irreversible. Even if a ship could return, it would return to a world that has moved on. This has implications for how such missions are justified. Are they acts of exploration or acts of seeding? Are they about visiting or about departing? The comfort relativity provides to travellers comes at the cost of severing them from the present of their origin. There is also a quieter implication. Relativity suggests that the universe is not designed to accommodate shared experiences across vast distances. It allows information and matter to move, but it fragments time in the process. Each world, each traveller, carries their own clock, their own pace of becoming. This fragmentation may be why interstellar civilizations, if they exist, do not easily interact. Even if they could travel, synchronizing intentions, goals and cultures across relativistic divides would be extraordinarily difficult. Time itself becomes a barrier to sustained interaction. Still, relativity does not say no outright. It does not forbid travel. It simply reshapes it into something unfamiliar. A journey that feels short but spans eras. A mission that succeeds locally but disconnects globally. As these ideas settle, the role of time becomes clearer. It is not just a measure of duration. It is a cost, a currency, and sometimes a consolation. Relativity allows us to spend time differently, but it does not let us avoid paying altogether. Energy is an unromantic word for something that quietly governs everything. It does not inspire in the way stars do, and it does not intimidate in the way black holes do. It simply sits underneath all motion, all change, all effort, enforcing rules without commentary. When interstellar travel is discussed seriously, stripped of optimism and spectacle, the conversation eventually collapses into energy. How much is needed, where it comes from, how it is stored, how it is controlled, and what it weighs. This is where many visions of travelling between stars finally lose their footing, not because energy is mysterious, but because it is relentlessly honest. It does not bend to enthusiasm. It does not care how important the destination feels. It only responds to equations that remain stubbornly the same no matter how badly we wish them to scale more gently. To move anything at all requires energy. To move it faster requires more. To move it for longer requires more still. These relationships are familiar on Earth. A heavier object takes more effort to lift. A faster car burns more fuel. A longer journey consumes more resources. But Earth quietly cushions these truths. Friction, gravity, and air resistance make energy losses feel intuitive. Space removes some of those losses, but it does not remove the accounting. In fact, space makes the accounting harsher. The first difficulty lies in acceleration. To reach interstellar speeds, a spacecraft must change its velocity dramatically. Even if it only accelerates once at the beginning and once at the end, the energy required for those changes dominates the mission. Cruising through space is cheap. Getting up to speed is not. Kinetic energy increases with the square of velocity. Double the speed, and the energy requirement quadruples. At relativistic speeds, the situation becomes even more severe, as energy increases faster than classical intuition suggests. This means that chasing speed quickly becomes an energy sink with diminishing returns. Now consider mass. A spacecraft is not just a shell. It contains structure, shielding, power systems, computers, instruments, life support if crewed, and redundancy for all of the above. Every kilogram adds to the energy bill, and the energy source itself has mass. Fuel is heavy, reactors are heavy, shielding is heavy, radiators are heavy. This leads to one of the most frustrating feedback loops in space engineering. You need energy to move mass, but your energy source adds mass, which requires more energy to move. There is no clever phrasing that makes this loop disappear. It must be managed, minimized, or accepted. Chemical fuels, the kind used in most rockets today, are particularly limited. They release energy through rearranging electrons in molecules. This is powerful enough to escape Earth's gravity, but weak on interstellar scales. The energy density simply does not compete with the demands of near-light speed travel. Nuclear fission improves the situation. It taps into energy stored in atomic nuclei rather than chemical bonds. This increases energy density by orders of magnitude. Nuclear thermal rockets and related concepts have been studied extensively, and they offer better performance than chemical propulsion. But better is not the same as sufficient. Even nuclear fission does not provide enough energy density to make relativistic interstellar travel practical for anything but very small payloads. The mass of fuel and shielding quickly overwhelms the benefit. Radiation hazards add further constraints. A powerful reactor must be isolated from crew and electronics, increasing distance and mass. Fusion, the process that powers stars, is often presented as the solution. In principle, fusion offers immense energy density. If controlled efficiently, it could outperform fission by a wide margin, but in practice, fusion remains elusive even as a stationary power source. Containing plasma, sustaining reactions, and extracting usable energy have proven far more difficult than early optimism suggested. Even if fusion propulsion were perfected, it would still not escape the mass energy accounting. Fusion fuel must be carried, reaction byproducts must be managed, waste heat must be radiated away. None of these problems vanish simply because the energy source is more powerful. Antimatter appears, on paper, to be the ultimate fuel. Matter and antimatter annihilate completely, converting nearly all mass into energy. The energy density is unmatched, but antimatter introduces problems so severe that it currently belongs more to thought experiments than engineering plans. Producing antimatter requires enormous amounts of energy. Storing it safely requires preventing contact with any normal matter, including container walls. Even tiny failures would result in violent energy release. Shielding against radiation from annihilation events adds mass, and the infrastructure required to generate meaningful quantities of antimatter would rival planetary-scale projects. Energy, it turns out, is not just about quantity. It is about control. High-energy systems produce heat. In space, heat cannot be carried away by air or convection. It must be radiated as infrared light. Radiators must be large and exposed. The The more power a system produces, the larger and more vulnerable these radiators become. This creates a design tension. Powerful engines demand large radiators. Large radiators add mass and surface area. Surface area increases the risk of damage from micrometeoroids and radiation. Damage reduces efficiency or causes failure. Failure is not easily repaired. Energy storage presents its own challenges. Batteries are heavy and degrade over time. Flywheels require precision and maintenance. Capacitors store limited energy. Nuclear systems provide continuous power but add complexity and risk. For long interstellar journeys, energy systems must function reliably for decades or centuries without resupply. There are no refueling stations between stars. Whatever energy infrastructure you launch with must be sufficient for the entire mission, or capable of using resources encountered along the way. This brings up the idea of harvesting energy en route. Could a spacecraft collect interstellar hydrogen and use it as fuel? Could it deploy massive sails to capture radiation pressure? Could it skim energy from stellar winds at the destination? Each idea has been studied, and each faces severe limitations. Interstellar space is extremely sparse. Hydrogen atoms are few and far between. Collecting meaningful quantities would require structures of enormous size, introducing drag, mass, and complexity. Radiation pressure is gentle, useful only over very long times and for very light objects. Even if energy could be harvested, conversion efficiency becomes critical. Every loss matters. Over long durations, inefficiencies compound. A system that is 99% efficient sounds impressive until you run it for decades and discover where the missing 1% went. Then there is the issue of deceleration. Energy problems do not end when you reach the destination. A spacecraft traveling at high speed carries enormous kinetic energy. To stop, that energy must go somewhere. It must be converted, dissipated, or transferred. Braking is not free. Using engines to decelerate requires carrying extra fuel from the start. Using stellar environments to brake requires precise navigation and introduces risk. Magnetic or electric braking concepts depend on conditions that may not be present or predictable. This means that a large fraction of a mission's energy budget may be devoted not to reaching the destination, but to avoiding overshooting it. The weight of all this cannot be ignored. Energy systems are heavy, structural supports are heavy, shielding is heavy, redundancy is heavy. The ship becomes an exercise in compromise, shaving grams here and there, balancing safety against feasibility. This is why discussions of interstellar travel often drift toward extremely small payloads, tiny probes, gram-scale sails, minimal systems. These reduce mass and energy requirements to something barely manageable, but they also reduce capability. A probe can observe. It cannot build, adapt, or sustain. Crewed missions amplify every energy problem. Life support requires continuous power. Heating, cooling, air circulation, water recycling, food production, waste management, and medical systems all consume energy. Psychological well-being adds indirect costs. Lighting, communication, recreation, and redundancy all draw from the same finite budget. And life support systems cannot be turned off. They are not optional. They run constantly, for as long as the crew lives. This means that interstellar travel with humans is not just about moving mass once. It is about sustaining an entire artificial environment indefinitely. Energy becomes the foundation not just of motion, but of existence. There is also the question of margins. On Earth, energy systems can fail gracefully. Power outages are inconvenient but rarely fatal. In space, especially far from any help, energy failure is existential. Without power, heating fails, life support fails, navigation fails, communication fails. The margin between functioning and catastrophe narrows dramatically. This forces designers to build in excess capacity. Excess capacity adds mass. Mass adds energy cost. The loop tightens again. What emerges from all this is not a single insurmountable obstacle, but a landscape where every path is steep. Energy does not forbid interstellar travel. It simply demands payment up front, in full, with interest compounded over time. The universe does not offer discounts for ambition, and yet energy constraints do something important. They force clarity, they prevent hand-waving, they turn vague dreams into specific questions. How much mass? How much power? For how long? At what risk? In answering those questions honestly, it becomes clear that the challenge is not just building better engines, but deciding how much we're willing to commit to moving anything at all between stars. Because energy is not just fuel, it is time converted into motion. It is resources converted into possibility. It is a measure of how much of ourselves we are willing to spend to reach somewhere else. Deep space has a reputation for emptiness. We picture it as a clean vacuum, a vast nothingness where objects drift untouched once they leave the clutter of planets and stars behind. That image is useful for poetry and misleading for engineering. Between stars, space is thin, but it is not gentle. It contains hazards that rarely announce themselves, hazards that do not explode or shine brightly, but work slowly and persistently, wearing down anything that travels through them long enough. These hazards are easy to underestimate precisely because they are subtle. A single encounter means nothing. A brief exposure leaves no obvious mark. But interstellar travel is not brief. It is measured in years, decades, or longer. And when time stretches, small dangers accumulate into defining constraints. Radiation is the most pervasive of these quiet threats. It is everywhere in deep space, arriving from multiple sources with different energies, directions, and effects. Unlike on Earth, where atmosphere and magnetic fields provide substantial protection, interstellar space offers little shelter. A spacecraft travelling between stars is exposed continuously, without pause, without refuge. Some radiation comes from the sun, especially during solar storms. This is already a concern for astronauts in near-Earth orbit and would remain relevant for missions leaving the solar system. But once a spacecraft moves far enough away, the sun becomes just another star and other sources begin to dominate. Cosmic rays are among the most serious. These are high-energy particles, mostly protons and atomic nuclei, accelerated to extreme speeds by distant supernovae, active galaxies, and other violent cosmic events. They move through the galaxy nearly at the speed of light, carrying enormous energy relative to their size. When a cosmic ray strikes matter, it does not simply stop. It initiates a cascade of secondary particles, a miniature shower that penetrates deeply into materials. Electronics can suffer bit flips. Sensors degrade. Structural materials slowly weaken at the atomic level. Biological tissue accumulates damage that increases cancer risk, impairs organs, and alters cellular processes. On Earth, most cosmic rays are absorbed or deflected before they reach the surface. In interstellar space, there is no such protection. Shielding can help, but shielding has limits. High-energy radiation can penetrate dense materials. Thick shields reduce exposure but add mass. Mass, as already discussed, is expensive to move. There is no perfect shield, only trade-offs. For uncrewed probes, radiation primarily threatens electronics. Over long durations, even hardened components degrade. Memory errors accumulate, sensors drift, power systems weaken. Designers can mitigate these effects through redundancy, error correction, and conservative design, but again, time magnifies every weakness. For crewed missions, radiation becomes a central concern. Chronic exposure over years or decades significantly increases health risks. Acute exposure from rare but intense events could be lethal. Shielding sufficient to protect humans for interstellar durations would likely be extremely heavy, adding yet another layer to the mass energy problem. Some proposals suggest using water, fuel, or other necessary materials as radiation shielding, placing them strategically around living areas. This helps, but it does not eliminate the issue. High-energy particles can still penetrate. Secondary radiation can be generated inside the shield itself. Protection is partial, not absolute. Then there is dust. Interstellar dust does not sound threatening. Individual grains are microscopic. They float sparsely through space. A single grain drifting harmlessly would never attract attention. But at interstellar velocities, speed changes everything. A dust particle impacting a spacecraft at a significant fraction of the speed of light carries enormous kinetic energy. Even at lower speeds, the energy involved is enough to damage surfaces, erode shielding, and puncture delicate components. At higher speeds, impacts become catastrophic. The frequency of such impacts is low, but over long journeys, low-probability events become likely. A spacecraft travelling for decades through interstellar space will encounter countless dust particles. Most will be tiny, some will not be. Protecting against dust impacts requires shielding that can absorb or deflect high-energy collisions. Whipple shields, layered structures designed to disperse impact energy, are used on spacecraft today. But scaling this approach to interstellar speeds and durations introduces serious challenges. Thicker shielding adds mass. Larger surface areas increase impact probability. Active deflection systems such as electromagnetic fields have been proposed, but their effectiveness against neutral particles and varied dust compositions remains uncertain. Energy requirements for maintaining such fields over long durations would be substantial. Dust also complicates optical systems. Telescopes, sensors, and communication equipment rely on exposed surfaces. Over time, impacts and erosion degrade performance. In interstellar space, there is no maintenance crew to clean lenses or replace components. Radiation and dust together create a slow, relentless wearing down. They do not destroy a ship in a single dramatic moment. They age it. They push systems toward failure gradually, quietly, often invisibly until thresholds are crossed. This gradual nature is what makes them so dangerous. Catastrophic failures are easier to design against. Slow degradation is harder. It demands foresight, conservative margins, and acceptance that some loss is inevitable. Deep space also contains plasma, magnetic fields, and charge particles that interact with spacecraft surfaces. These interactions can cause charging effects, leading to electrical discharges that damage components. Over long periods, repeated charging and discharging stresses materials and electronics. Thermal extremes add another layer. Interstellar space is cold, but not uniformly so. Exposure to starlight, internal heat sources, and radiation creates temperature gradients. Materials expand and contract. Joints fatigue. Insulation degrades. Thermal cycling over decades contributes to structural wear. Then there is the biological side, which extends beyond radiation. Long-term exposure to microgravity affects bones, muscles, cardiovascular systems, and fluid distribution. While some of these effects can be mitigated through artificial gravity or exercise, implementing such systems over interstellar durations adds complexity and energy demand. Isolation compounds these issues. Medical care must be autonomous. Surgical interventions, diagnostics, and treatment must be possible without external support. Supplies must last or be recycled perfectly. Psychological stress interacts with physical health in ways that are difficult to predict over long timescales. Even uncrewed missions face a form of biological hazard in the sense that any life detection experiments must remain uncontaminated. Radiation can alter organic molecules. Dust impacts can introduce foreign material. Preserving scientific integrity becomes harder as exposure accumulates. One of the most challenging aspects of these hazards is that they cannot be eliminated by clever shortcuts. You cannot negotiate with cosmic rays. You cannot avoid dust entirely. You can only reduce exposure, manage damage, and hope that systems last long enough. This makes interstellar travel fundamentally different from most human engineering projects. It is not about reaching a destination quickly and then dealing with challenges upon arrival. It is about surviving the journey itself, which is the dominant phase of the mission. On Earth, journeys are usually brief relative to their purpose. You travel for hours to attend a meeting that lasts days. You sail for weeks to reach land where you settle for years. In interstellar travel, the journey is the majority of the experience. The destination is a narrow window at the end. This inversion changes priorities. Durability matters more than performance. Reliability matters more than speed. Predictability matters more than flexibility. Radiation, dust, and other quiet hazards reward conservative design and punish optimism. They do not care about intentions or goals. They respond only to exposure time and material limits. Some researchers propose that the solution is to avoid sending complex systems at all. Instead, send extremely simple probes that can tolerate damage and still function. Others suggest sending many probes, accepting that most will fail but hoping some will succeed. This shifts the problem from individual reliability to statistical survival. These approaches may work for limited scientific exploration. They do not scale easily to crude missions or complex operations. Humans require stable environments. They do not tolerate gradual degradation well. Another idea is to shorten exposure by increasing speed. But as discussed earlier, higher speed increases the severity of radiation and dust impacts. Faster travel reduces time but increases intensity. The total dose may not decrease as much as hoped. There is no easy optimization. Every adjustment trades one risk for another. It is also worth noting that these hazards do not end upon arrival. The space around other stars can be more hostile than our own. Stellar activity, radiation belts, and unknown environments introduce new uncertainties. A ship that survives the journey may arrive already weakened, facing fresh challenges with limited reserves. This cumulative nature of deep space hazards reinforces a broader pattern. Interstellar travel is not blocked by a single wall. It is eroded by many small forces acting together over long periods. Each one alone seems manageable. Together, they become decisive. And yet, these hazards also teach something important. They reveal that the universe is not empty in the way we often imagine. It is active, energetic, and dynamic, even in its quietest regions. Travelling through it is not like crossing a calm sea, but like enduring a constant low-level storm that never fully breaks. As attention lingers on these risks, another question naturally arises. Even if a spacecraft could be shielded perfectly, even if systems could endure radiation and impacts indefinitely, what about the passengers themselves? The idea of sending humans between stars often focuses on machines, engines, and trajectories, but beneath all of that sits a quieter and far more delicate variable: the human organism. Not as an abstract concept, but as a living system shaped by gravity, sunlight, social contact, and rhythms that evolved over millions of years on a single planet. When journeys stretch from months into decades and beyond, the question stops being whether a ship can survive the voyage and becomes whether the people inside it can remain whole while doing so. The human body is remarkably adaptable in the short term. It tolerates stress, heals from injury, and adjusts to new environments with surprising resilience. This adaptability has enabled humans to live in deserts, polar regions, high mountains, and sealed space stations. But adaptability is not infinite, and it is not evenly distributed across time. What the body can endure for weeks or months is not necessarily what it can endure for years, and what it can survive for years may still leave lasting damage. Microgravity is one of the most immediate concerns. In orbit, astronauts experience bone density loss, muscle atrophy, changes in cardiovascular function, and shifts in fluid distribution. Exercise regimes can slow these effects, but they do not fully prevent them. After months in microgravity, returning to Earth requires rehabilitation. After years, the damage becomes harder to reverse. Artificial gravity, usually proposed through rotating habitats, is often suggested as a solution. In principle, it can simulate gravitational forces and mitigate many physical issues. In practice, building a reliable, long-duration rotating system introduces new engineering challenges. Structural stresses, motion sickness, mechanical wear, and energy requirements all increase. And even artificial gravity may not perfectly replicate Earth's conditions, especially over decades. Radiation adds another layer. As discussed earlier, deep space exposes travelers to chronic radiation that accumulates over time. For the human body, this means increased cancer risk, damage to the nervous system, and potential effects on fertility and development. Shielding can reduce exposure but rarely eliminate it. Over very long voyages, cumulative dose becomes a central concern. Sleep cycles are also disrupted. On Earth, circadian rhythms are synchronized with the day-night cycle. In space, especially far from stars, light cues must be artificially managed. Even small disruptions can compound over time, affecting mood, cognition, and immune function. Long-term circadian misalignment has been linked to a range of health issues on Earth, and there is little reason to believe deep space would be kinder. Nutrition must be managed perfectly. Closed-loop food systems would need to recycle nutrients efficiently, maintain variety, and prevent deficiencies. Even minor imbalances, if sustained over years, could lead to serious health problems. Food is not just fuel. It is cultural, emotional, and social. Monotony alone can become a psychological stressor. Then there is aging itself. Even if time dilation reduces subjective duration for travelers at high speeds, aging still occurs according to the traveler's own clock. A crew embarking in early adulthood may arrive middle-aged or older. Physical capacity changes, cognitive flexibility shifts. Long missions must account for life stages, not just mission phases. Medical care presents another challenge. On Earth, healthcare relies on specialization, external supply chains, and emergency evacuation. None of these exist between stars. A spacecraft must carry the equipment, knowledge, and autonomy to handle everything from minor injuries to major surgery, from infections to chronic disease management. Medical technology also ages. Devices become obsolete. Software becomes outdated. Consumables degrade. Planning for medical self-sufficiency over decades requires anticipating conditions and technologies that may not even be known at launch. All of this addresses the body. The mind introduces a different kind of fragility. Humans are social organisms. Our brains evolved in environments rich with interaction, novelty, and feedback. Long-term isolation, confinement, and monotony place unusual strain on mental health. Even in short-duration missions, astronauts report mood changes, interpersonal tension, and cognitive fatigue. Over interstellar timescales, these effects could become defining. Isolation is not just about being alone. It is about being cut off from meaningful novelty and unstructured choice. A spacecraft, no matter how well designed, is a closed environment. The same walls, the same routines, the same people. Over years, this can erode motivation and emotional regulation. Confinement amplifies conflict. Minor disagreements that would dissipate in open environments can linger and intensify when escape is impossible. Social dynamics become critical. Crew selection, training, and psychological compatibility matter as much as technical skill. Even then, predicting long-term interpersonal outcomes is notoriously difficult. There is also the issue of purpose. Humans tolerate hardship better when it feels meaningful. On an interstellar mission, the payoff is distant and abstract. Daily tasks may feel disconnected from the ultimate goal. Maintaining a sense of agency and relevance over decades requires careful design of roles, feedback, and autonomy. Communication delays worsen this. Conversations with Earth become asynchronous, delayed by years. Support becomes historical rather than immediate. Advice arrives too late. News from home reflects a world that has already moved on. The psychological anchor of belonging weakens. This can produce a sense of temporal dislocation. Travellers live in a different now than everyone else. Their present does not align with the present of their origin world. Over time, this can erode identity. Who are you if the society you came from no longer exists in a recognisable form? Memory plays a role here. Long voyages mean that memories of Earth become increasingly distant, both temporally and emotionally. New generations, if born aboard, may have no direct connection at all. Their sense of home is the ship, not the planet that launched it. For generation-style missions, this becomes a central issue. Children born during the journey did not choose the mission. Their consent is implied rather than given. Their lives are defined by a destination they may never see or care about. This raises ethical questions that cannot be resolved by engineering. Education aboard such a vessel must serve two purposes at once. It must prepare individuals to maintain the ship and fulfill the mission, and it must provide a meaningful life independent of that mission. Balancing these goals over generations is not trivial. Cultural drift is inevitable. Values change, priorities shift, traditions evolve. Over time, the original mission goals may lose relevance or be reinterpreted. This is not a failure of discipline, it is a natural property of human societies. Even for shorter, crewed missions, psychological health remains fragile. Depression, anxiety, and cognitive decline are not just individual problems. They affect group dynamics and decision-making. A single severe psychological crisis could destabilize an entire mission. Countermeasures exist. Structured routines, access to virtual environments, creative outlets, and psychological support systems can help. Artificial intelligence companions are sometimes proposed to provide interaction and monitoring, but none of these are proven over interstellar durations. There is also the risk of complacency. Long periods without incident can breed overconfidence or boredom. Attention lapses, procedures become routine. In high-risk environments, this can be dangerous. Maintaining vigilance without constant stimulation is a known challenge even in much shorter missions. The human mind is also sensitive to uncertainty. Interstellar travel involves long periods where nothing happens, punctuated by moments of high consequence. This uneven rhythm can be stressful. Anticipation without resolution can wear down resilience. Sleep disturbances compound everything. Poor sleep affects mood, cognition, immune function, and interpersonal behavior. In closed environments, sleep quality can degrade subtly over time, creating a feedback loop of declining performance and well-being. Another often overlooked factor is grief. Over long missions, travellers may lose loved ones on Earth. News arrives late. There is no opportunity for closure in familiar ways. Grieving at a distance, years removed from events, in an environment that cannot change, presents psychological challenges that are difficult to simulate. Then there is fear. Not acute fear, but background awareness. The knowledge that you are far from help. That mistakes cannot be undone easily. That survival depends on systems you cannot fully control. This awareness may fade into the background, or it may persist, shaping behaviour and mental health in subtle ways. Some people thrive under such conditions, others do not. Predicting who will fall into which category over decades is uncertain at best. Selection processes can reduce risk, but they cannot eliminate it. What emerges from all of this is a picture where the human element is not a secondary concern, but a central constraint. Bodies degrade, minds strain, societies drift. These are not failures of willpower or training. They are natural consequences of placing a terrestrial species into an environment that stretches far beyond its evolutionary context. This does not mean humans cannot travel between stars. It means that doing so would fundamentally change what it means to be human during the journey. Lives would be lived under conditions that have no historical precedent. Identity, purpose, and health would all be negotiated anew. When the distances between stars refuse to shrink, and when individual lifespans refuse to stretch far enough to bridge them, the idea of the generation ship begins to surface almost inevitably. It does not arrive with excitement or speed. It arrives slowly, as a concession, a recognition that if humans are ever to travel between stars without relying on speculative physics, the journey itself must become a place to live, not merely a path to endure. A generation ship is not really a spacecraft in the familiar sense. It is closer to a moving habitat, a sealed world carrying a population across interstellar space over many human lifetimes. The people who arrive at the destination are not the people who left. In many cases, they may not even remember the departure except through stories, records, and rituals. Their entire existence unfolds in transit. This concept is often presented as a solution to the problem of time. If a journey takes hundreds or thousands of years, then instead of trying to compress that duration into one lifespan, you allow lifespans to unfold naturally within it. Birth, life, and death all occur aboard the vessel. Time is no longer something to be beaten. It is something to be inhabited. On the surface, this seems practical. Humans have lived in closed environments before, on islands, in polar stations, in submarines and space stations. We already know how to build life support systems, recycle water, manage air, and grow food in controlled conditions. Extend these systems, scale them up, and make them more robust, and perhaps a self-sustaining world could drift between stars. But the deeper you examine the idea, the more it becomes clear that generation ships are not merely engineering projects. They are social experiments of unprecedented scale and duration. Every technical challenge is entangled with ethical, cultural, and psychological ones. The ship must not only function, it must remain livable, meaningful, and stable across generations that never chose the mission for themselves. The first and most immediate issue is population size. A generation ship must carry enough people to maintain genetic diversity over many generations. Too few, and inbreeding becomes a serious risk. Genetic drift, the random loss of variation, can accumulate quietly until health problems emerge. Estimates for a viable minimum population vary, but most suggest thousands rather than hundreds. A larger population improves genetic stability, but it increases resource demands. More food, more water, more space, more waste, more complexity. The ship grows in size and mass, making every other engineering problem harder. Structural integrity, shielding, energy production, and propulsion all become more demanding. Then there is reproduction itself. On Earth, reproduction is a personal choice shaped by culture, economics, and individual desire. On a generation ship, reproduction becomes a system-level concern. Birth rates must be managed to prevent overpopulation or population collapse. This implies regulation, whether explicit or implicit, of deeply personal decisions. Any system that governs who can have children, when and how many, carries ethical weight, even if implemented gently, through incentives rather than force. It shapes lives in fundamental ways. Over generations, such systems can breed resentment, resistance, or reinterpretation. Children born aboard a generation ship inherit a reality they did not choose. Their sky is metal, their horizon is a corridor, their planet is a machine. For them, Earth is not home. It is an ancestral concept, like a mythic origin story. Their sense of belonging is tied to the ship itself. This raises a difficult question. Is the ship a means to an end, or is it the end? For the first generation, the destination star system may be the purpose. For later generations, especially those born centuries into the journey, that purpose may feel abstract or irrelevant. Their lives are full already. Why uproot again? Maintaining commitment to a distant destination across generations requires more than instructions. It requires culture, stories, education, shared meaning. The mission must be woven into identity. not just documented in archives. History shows how difficult this is even over much shorter timescales. Cultural values shift, priorities change, traditions evolve. The reasons one generation finds compelling may not resonate with the next. On a generation ship, there is no external reference to stabilize these shifts. Everything happens in isolation. Governance becomes a central concern. A generation ship must have systems for decision-making, conflict resolution, and leadership that can adapt over centuries. No single political structure is guaranteed to remain stable indefinitely. Monarchies fall, democracies fracture, technocracies stagnate. The ship must be resilient not just to mechanical failure, but to social transformation. Power dynamics will emerge naturally. Control over resources, information, or critical systems confers influence. If unchecked, this can lead to inequality or authoritarianism, but rigid control risks rebellion. Balancing stability and freedom in a closed system is one of the hardest problems in political philosophy, and a generation ship offers no escape valve. Education is another long-term challenge. Knowledge must be preserved accurately across centuries. Skills must be transmitted reliably. Misunderstandings, myths, and simplifications can creep in over time. If technical knowledge degrades, the ability to maintain the ship erodes. Even written records are not immune. Languages change, context is lost. Instructions that seem clear to one generation may be misinterpreted by another. Without careful curation, essential systems could become opaque, maintained by ritual rather than understanding. There is also the issue of innovation. A society frozen entirely in service of a mission risks stagnation. Yet uncontrolled innovation could alter systems in unforeseen ways, potentially endangering the ship. Deciding what can change and what must remain fixed becomes an ongoing negotiation. Psychological health takes on new dimensions in a generation ship. Individuals grow up knowing there is no outside world to visit, no wider society to join, no alternative environment. This can produce strong community bonds, but it can also create claustrophobia, rebellion, or apathy. Some individuals may struggle with the idea that their entire life will be spent in transit, working toward a goal they will never personally experience. Others may reject the destination entirely, viewing the ship itself as the only meaningful world. If a significant portion of the population loses faith in the mission, what happens? Is dissent tolerated? Is the destination optional? Can the ship turn back? These questions have no easy answers, and distance ensures that choices are final. Death also takes on a different character. Every person who dies aboard a generation ship is buried in transit. Cemeteries, memorials, and rituals must exist within the ship's finite space. Grief accumulates alongside population growth. Memory becomes layered and dense. Over time, the ship itself becomes a historical artifact. Walls bear the marks of generations. Systems carry modifications layered atop modifications. The original design recedes into the past, replaced by lived reality. One of the most unsettling aspects of generation ships is the absence of consent. The first generation may volunteer. Later generations cannot. They are born into obligation. Philosophers have debated whether it is ethical to impose such a destiny, even in the service of survival or exploration. Some argue that all societies impose conditions on their children. No one chooses where they are born. A generation ship is simply a more extreme version of this. Others counter that the stakes are higher, the constraints tighter, and the alternatives fewer. There is also the possibility of mission failure long after departure. A critical system might degrade beyond repair. A social collapse could destabilize governance. A cascade of small errors could render the destination unreachable. In such a case, entire generations may live and die, knowing that the promised future will never arrive. This is not an argument against generation ships. It is an acknowledgement of what they are. They are not vehicles, they are commitments, They trade speed for continuity, distance for time, and individual choice for collective endurance. From a purely physical perspective, generation ships are among the most conservative interstellar concepts. They rely on known physics. They do not require breaking speed limits or manipulating space-time. In that sense, they may be the most realistic option available. But realism comes with weight. The weight of managing human lives across centuries. The weight of building not just machines, but societies that can persist without external input. The weight of accepting that arrival is uncertain, and meaning must be sustained regardless. In a quiet way, generation ships force a redefinition of what interstellar travel means. It is no longer about going somewhere else. It is about becoming something else along the way. A culture shaped by motion, isolation, and delayed horizons. And as that idea settles, another question begins to form naturally. If living entire lives in transit is so demanding, is there a way to suspend life itself? The appeal of sleeping through a long journey is almost instinctive. When distance stretches beyond patience and time becomes an enemy rather than a companion, the idea of simply skipping the waiting feels like a relief. Close your eyes, pause the body, let centuries pass unnoticed. Wake up near another star as if the intervening emptiness never happened. Compared to the burdens of generation ships and the strain of long conscious voyages, cryosleep sounds clean, efficient, and merciful. That sense of mercy is exactly why the concept returns again and again in discussions of interstellar travel. It promises a way around the human problem without redefining humanity itself. No societies drifting in transit. No children born into obligation, no centuries of psychological erosion, just individuals stepping across time in controlled suspension. But cryosleep, or suspended animation, sits in an uncomfortable space between biology, medicine, and wishful thinking. It is not forbidden by any single law of physics, yet it resists implementation at every practical level. The science is incomplete, the risks are poorly bounded, and the gap between short-term laboratory success and long-duration human application remains wide. To understand why, it helps to separate the idea from its fictional shorthand. Cryosleep is not simply freezing someone and waking them later. Biological systems are not water bottles. They are complex arrangements of cells, proteins, membranes, electrical gradients, and chemical balances that depend on constant regulation. Interrupting that regulation without destroying structure is extraordinarily difficult. Freezing is the most intuitive approach, and also the most dangerous. When water freezes, it expands and forms crystals. Inside cells, ice crystals rupture membranes, disrupt organelles, and shred delicate structures. Even small amounts of intracellular ice can be fatal. Nature solves this problem only in limited cases, such as certain insects, frogs, and microorganisms that can tolerate freezing through specialized biochemistry. Humans do not possess these adaptations. Cryoprotectants, substances that reduce ice formation, can mitigate some damage. They are used successfully to preserve small samples like embryos, sperm, and certain tissues. But scaling this up to entire organs, let alone whole bodies, introduces new problems. Cryoprotectants can be toxic. They must be distributed evenly. Removing them safely after thawing is as challenging as introducing them. Even if freezing damage could be avoided, temperature itself is not the only issue. Cells rely on gradients of ions, on electrical potentials across membranes, on finely tuned chemical concentrations. Cooling slows reactions, but it does not halt all processes uniformly. Some reactions continue longer than others, leading to imbalances that worsen over time. There is also the issue of time itself. Cryopreservation works best when the frozen period is relatively short. The longer a biological system remains suspended, the more opportunities arise for slow chemical changes, radiation damage, and molecular decay. Over years or decades, even small rates of damage accumulate. Deep space does not pause these processes. Radiation continues to pass through frozen tissue. DNA can still suffer breaks. Proteins can still degrade. Without active repair mechanisms which require metabolism, damage accrues silently. Cryosleep reduces the rate of harm, but it does not eliminate it. Some researchers propose vitrification rather than freezing. In vitrification, tissues are cooled so rapidly and with such high concentrations of cryoprotectants that they form a glass-like solid rather than crystalline ice. This avoids ice damage, but introduces other challenges. Achieving uniform vitrification in large volumes is extremely difficult. Thermal stresses can crack tissues. Cryoprotectant toxicity remains a concern. Then there is rewarming. Cooling biological systems is only half the problem. Waking them back up intact is equally complex. Uneven warming can cause thermal gradients that damage tissues. Metabolic processes must restart in a coordinated way. Organs must resume function simultaneously. A heart that restarts too early or too late relative to other systems can fail catastrophically. In small-scale experiments, researchers have achieved limited successes. Certain animals can be cooled to near-freezing temperatures and revived. Some organs have been preserved and transplanted after cold storage. Emergency medicine has explored induced hypothermia to slow metabolism during trauma. These are real achievements, but they operate on timescales of minutes or hours, not years. Scaling cryosleep from hours to decades is not a matter of incremental improvement. It is a qualitative leap. It requires not only preventing immediate damage, but ensuring long-term molecular stability in an environment filled with radiation and uncertainty. Even if the biological hurdles were overcome, cryosleep introduces operational challenges. A sleeping crew cannot respond to emergencies. Systems must function autonomously. Failures that occur during suspension may go unnoticed until revival is attempted, at which point it may be too late to intervene. This demands extremely reliable monitoring systems capable of detecting and correcting problems without human oversight. Such systems would need to manage life support, thermal regulation, radiation shielding, and mechanical integrity continuously. They would also need to diagnose subtle biological issues that even awake humans struggle to detect. There is also the question of staggered versus simultaneous suspension. Waking everyone at once increases risk. Staggered waking allows monitoring and assistance, but requires some crew to remain awake for long periods, reintroducing the psychological burdens cryosleep was meant to avoid. Ethical questions arise as well. Cryosleep involves placing individuals into a state of extreme vulnerability. They cannot consent dynamically. They cannot respond to changing conditions. Decisions made before suspension govern years or decades of exposure. Trust in systems and planners must be absolute. Consent becomes even more complicated when suspension spans long durations. If something goes wrong halfway through a journey, the sleepers cannot reassess their willingness to continue. They are passengers in the most literal sense. There is also the issue of identity. Long-term suspension interrupts continuity of experience. From the sleeper's perspective, time passes instantly. From the outside, years or centuries unfold. This temporal discontinuity raises philosophical questions about personal identity and responsibility, especially if societal contexts change dramatically during the sleep. From a medical standpoint, there is uncertainty about long-term effects. Even if revival is successful, subtle neurological or psychological changes may occur. Memory, personality, and cognitive function could be altered. Without long-term studies, these risks remain unknown. Cryosleep also does not solve all human factors. Upon waking, individuals must adapt quickly to new environments, new social contexts, and potentially new cultures. There is no gradual acclimatization. Psychological shock is possible. Trauma may arise from sudden dislocation in time. From an engineering perspective, cryosleep reduces life support demands during transit. but does not eliminate them. Temperature control, radiation shielding, and structural integrity remain essential. Energy systems must operate continuously. Failures during suspension may be harder to detect because biological feedback is minimal. There is also a false sense of simplicity associated with cryosleep. It feels like a clean workaround, but it shifts complexity rather than removing it. Instead of managing conscious humans over long durations, you must manage dormant humans perfectly. The tolerance for error becomes even smaller. It is telling that cryosleep is more developed in fiction than in laboratories. Stories can assume perfect suspension and revival. Reality cannot. Every assumption must be tested, validated, and repeated under conditions far harsher than those of Earth-based experiments. That does not mean cryosleep is impossible. It means it is unfinished science. The gap between what is conceptually allowed and what is practically achievable remains large. Closing that gap would require advances in cryobiology, nanotechnology, medicine, and autonomous systems far beyond current capabilities. Some researchers speculate about nanotechnological repair, microscopic machines that could fix damage at the cellular level during or after suspension. This idea is elegant but speculative. Building such systems would require mastery of biology and engineering at scales we do not yet control. Others suggest combining cryosleep with time dilation, reducing subjective duration further. This compounds complexity rather than reducing it. High speeds increase radiation exposure and impact risk. Cryosleep mitigates some biological effects, but not all. There is also the question of failure modes. What happens if suspension fails partially? If some individuals revive damaged? If systems degrade unevenly? Planning for these contingencies is difficult because there is no real-world data to draw from. From a mission design perspective, cryosleep shifts risk from the journey to the wake-up moment. Instead of continuous risk spread over decades, you concentrate risk at revival. That moment becomes critical. Everything depends on it working correctly. This concentration of risk may or may not be acceptable, depending on philosophy. Some may prefer a long period of managed difficulty to a single high-stakes event. Others may choose the opposite. Cryosleep also does nothing to reduce distance itself. It shortens subjective experience, not objective travel time. Communication delays remain. Cultural drift at the destination remains. The universe still ages while sleepers do not. In that sense, cryosleep is less a solution to interstellar travel than a coping mechanism. It allows humans to endure what would otherwise be intolerable. It does not make the journey easier for the universe. It makes it easier for the traveller. This distinction matters. Many of the challenges discussed earlier, energy, radiation, reliability, navigation, remain unchanged. Cryosleep interacts with them, but does not erase them. What it does offer is a narrowing of the human problem. Instead of supporting lives continuously, you preserve them. Instead of managing societies in transit, you manage systems. This is attractive to engineers and planners because systems feel more controllable than people. But biology resists simplification. Human bodies are not passive cargo. They are dynamic systems with needs that do not disappear simply because consciousness is paused. As research continues, cryosleep remains a field of promise and frustration. Incremental progress is real. Preservation techniques improve. Understanding deepens. But the leap from preserving cells and organs to preserving whole humans for interstellar durations remains unbridged. And even if that bridge were built, it would not settle the larger question. Cryosleep would change how journeys feel, not what they mean. It would allow individuals to step across time, but it would not guarantee that what they wake up to aligns with what they left behind. When familiar solutions begin to fail, imagination looks for exits in less familiar places. If distance cannot be reduced, if speed cannot be increased beyond a hard limit, and if biology resists being paused indefinitely, then attention naturally drifts toward the structure of space itself. Instead of asking how to move faster through the universe, the question becomes whether the universe can be persuaded to rearrange itself around the traveller. This is where ideas like warp drives and wormholes enter the discussion. They arrive wearing the language of advanced physics, supported by real equations, yet hovering in a strange zone between what mathematics permits and what nature may actually allow. They are not pure fantasy, but neither are they engineering plans. They are possibilities on paper, elegant constructions that hint at shortcuts through space-time, while quietly hiding conditions so extreme that realization remains uncertain at best. Warp drives begin with a simple conceptual shift. Instead of pushing a spacecraft through space, you manipulate space itself. Space contracts in front of the vessel and expands behind it, creating a moving bubble. Inside that bubble, the ship is locally at rest. It never violates the speed limit in its immediate surroundings, but relative to distant observers, the bubble can move arbitrarily fast, effectively carrying the ship across vast distances in short external time. This idea is not pulled from thin air. In the mathematics of general relativity, space-time is flexible. It can curve, stretch, and compress in response to energy and mass. The same equations that describe black holes and expanding universes also allow, in principle, configurations where space-time itself flows. One such configuration is often referred to as a warp metric. It is a specific solution to Einstein's equations that describes a region of space-time moving faster than light, relative to its surroundings, without requiring anything inside that region to locally exceed the speed of light. From a purely mathematical standpoint, it is internally consistent. That consistency is what makes warp drives so tempting. They appear to sidestep the universe's speed limit without breaking it. No infinite energy required to accelerate mass to light speed. No relativistic penalties applied to the ship itself. The universe is not outrun, it is reshaped. But the cost of this reshaping is where the daydream begins to unravel. Warp metrics require exotic energy conditions. Specifically, they require regions of negative energy density. Not just small amounts, but large sustained regions where energy behaves in ways never observed in nature. Negative energy is not the same as antimatter or empty space. It is a property where the energy of a region is lower than the vacuum itself. In quantum physics, small, fleeting amounts of negative energy can exist under very specific circumstances. These effects are subtle, localized, and tightly constrained. Scaling them up to macroscopic, controllable structures capable of shaping space-time is a leap of many orders of magnitude. Even optimistic estimates suggest that the amount of negative energy required to sustain a warp bubble would be comparable to the mass energy of planets or stars. More conservative calculations push that requirement far beyond anything imaginable, and this energy must be arranged with exquisite precision. Slight deviations could destabilize the bubble potentially catastrophically. Then there is the issue of control. Creating a warp bubble is only part of the problem. You must also steer it, start it, stop it, and keep it stable. General relativity allows exotic solutions, but it does not provide simple mechanisms for manipulating them. The equations describe what could exist, not how to build or maintain it. There are also troubling implications for causality. Faster-than-light effective travel allows for scenarios where cause and effect become ambiguous. Events could influence their own pasts. Different observers could disagree on the order of events in ways that cannot be reconciled. While some physicists argue that global consistency conditions might prevent paradoxes, this remains speculative. Warp drives also pose hazards to anything outside the bubble. The compression and expansion of space-time would interact with surrounding matter and radiation. Calculations suggest that intense energy could build up at the front of the bubble, potentially releasing destructive bursts upon deceleration. Arriving at a destination might be far more violent than intended. Even assuming all of these issues could be managed, warp travel introduces another subtle problem. It isolates the traveller from the universe in unusual ways. Signals cannot easily enter or leave the bubble. Navigation becomes complex. You may move quickly, but you're cut off from feedback. In short, warp drives replace one set of problems with another, often more severe set. They are not forbidden, but they are fantastically demanding. Wormholes take a different approach. Instead of reshaping space dynamically, they propose permanent or semi-permanent shortcuts. A wormhole connects two distant regions of space-time through a tunnel-like structure. Enter one mouth, exit the other, regardless of the distance in normal space. Like warp drives, wormholes arise naturally as solutions to Einstein's equations. They are mathematically allowed. In certain cases, they even appear as natural consequences of specific space-time geometries. But like warp drives, they demand exotic conditions to remain open and traversable. Without intervention, most wormholes collapse too quickly for anything to pass through. To keep one open, negative energy is again required. The same problems arise. Large quantities, precise control, stability over time. There is also the question of origin. Where do wormholes come from? Can they be created artificially, or must they be found? If found, can their endpoints be moved? Each of these questions opens further layers of uncertainty. Even if a stable wormhole existed, using it for interstellar travel introduces risks. The gravitational environment inside a wormhole could be extreme. Tidal forces might stretch or compress matter. Radiation levels could be high. Navigation inside the tunnel may be impossible in any familiar sense. Then there is the matter of time. Wormholes do not merely connect points in space. They can connect points in time. Under certain conditions, a wormhole can act as a time machine, allowing travel into the past relative to one endpoint. This again raises causality concerns that physics has not fully resolved. Some physicists suspect that the universe may enforce consistency by preventing such configurations from forming or persisting. This idea, sometimes referred to as chronology protection, suggests that while equations permit exotic structures, nature itself may disallow them through mechanisms we do not yet understand. This suspicion is fueled by the absence of observational evidence. Despite extensive astronomical surveys, no clear signs of natural wormholes or warp-like phenomena have been found. The universe appears remarkably conservative in its large-scale behaviour. It expands, it curves, it forms black holes, but it does not appear to offer ready-made shortcuts. There is also a practical consideration often overlooked in popular discussions. Even if a warp drive or wormhole could be created, doing so would not automatically solve interstellar travel as we imagine it. Infrastructure would be required, energy generation on unimaginable scales, construction capabilities beyond any current projection. A single shortcut is not enough. To be useful, such systems would need to be repeatable, reliable, and safe. They would need to integrate with navigation, communication, and safety protocols. The complexity rivals that of building entire civilizations around new physical principles. This is why many physicists treat warp drives and wormholes as valuable thought tools rather than actionable plans. They help probe the limits of our theories. They reveal what general relativity allows and where it strains. They expose tensions between gravity, quantum mechanics, and causality. In that sense, they are not failures. They are stress tests for our understanding of the universe. It is also important to note that mathematics alone does not guarantee physical existence. History is full of solutions that are mathematically consistent but physically irrelevant. Nature chooses which equations it realizes, and it does so without explanation. The universe may permit shortcuts on paper, while refusing to manifest them in reality. This possibility leads to a sobering conclusion. The most dramatic solutions to interstellar travel may be the least attainable. The closer an idea comes to eliminating all constraints, the more likely it is to require conditions that cannot be met. Warp drives and wormholes are appealing because they promise escape. Escape from distance, escape from time, escape from biology, but escape itself may be the wrong frame. The universe does not seem designed for escape, it seems designed for persistence. This does not mean such ideas should be dismissed. Research into exotic space-time structures continues to yield insights. Constraints are refined, assumptions are challenged. Occasionally small revisions reduce the severity of requirements, but even optimistic developments leave these concepts far beyond foreseeable engineering, and so these ideas remain where they are most comfortable, in equations, in papers, in conversations that explore possibility without commitment. They remind us that the universe is stranger than intuition suggests, but also more disciplined than imagination prefers. There is a subtle shift that happens once enough barriers have been examined. At first, the obstacles to interstellar travel feel technical. Engines are insufficient. Energy demands are extreme. Biology is fragile. Time stretches uncomfortably. But after moving through all of these layers, a quieter question begins to emerge, one that is less about machinery and more about pattern. When so many independent difficulties point in the same direction, it becomes reasonable to ask whether this is coincidence, or whether the universe itself is structured in a way that gently but persistently discourages leaving home. This is not a question about intention. The universe does not have motives in any human sense. It does not want or forbid. But it does have laws, regularities, and large-scale structures that shape what is easy, what is hard, and what is effectively unreachable. And when those structures repeatedly funnel complexity inward rather than outward, it can feel as though exploration beyond a certain scale is not just difficult, but subtly resisted. The first hint comes from scale itself. Planetary systems are dense with opportunity. Moons, asteroids, comets, and planets offer resources, energy gradients, and varied environments. Within a single star system, there is enough material to support civilizations far more advanced than our own for very long periods. Fusion fuel, metals, volatiles, and habitable real estate are abundant on astronomical timescales. From a purely practical standpoint, a civilization does not need to leave its star system to thrive. Beyond that system, the universe changes character. Distances explode. Matter thins out. Energy sources become sparse. The ratio between effort and reward shifts dramatically. It is as if complexity is clustered locally, while emptiness dominates globally. This clustering is not accidental. Stars form from dense molecular clouds. Planets form from disks of material around those stars. Life, if it arises, does so on worlds where chemistry is rich and conditions are stable. All of this happens in pockets. Between pockets, there is very little. The universe, in other words, is granular. It is built from islands separated by vast oceans of near nothing. Travel within islands is manageable. Travel between them is not. Physics reinforces this structure. The speed limit prevents rapid crossing of emptiness. Energy costs rise steeply with velocity. Radiation fills the gaps. Time dilation fragments shared experience. None of these effects are arbitrary. They all emerge from the same underlying framework. They all scale in ways that favour local interaction over distant reach. Even information obeys this pattern. Signals travel freely but slowly. Observation is easy. Presence is not. You can see far more than you can touch. This raises an intriguing possibility. Perhaps the universe is optimized for observation rather than expansion. Knowledge spreads, influence does not. Civilizations may become astronomically aware long before they become astronomically mobile. From this perspective, the silence between stars takes on a different meaning. It is not necessarily a sign that no one is out there. It may simply reflect that no one travels. This idea connects naturally to questions about extraterrestrial civilizations. For decades, people have wondered why, if intelligent life is common, the galaxy does not show obvious signs of visitation or colonization. This is often framed as a paradox, an apparent mismatch between probability and observation. But if interstellar travel is as costly and unattractive as it appears, the paradox softens. Civilizations may arise, develop technology, explore locally, and then plateau. Not because they fail, but because further expansion offers diminishing returns. A civilization that masters its own star system gains access to energy on a stellar scale. It can build habitats, manipulate matter, and sustain itself for time spans far longer than biological evolution requires. Compared to that, sending fragile vessels across light years of emptiness may seem unnecessary. The universe does not block the door. It simply makes staying inside more appealing. There is also the matter of risk. Every step outward multiplies uncertainty. Unknown environments, unpredictable hazards, long delays, irreversible commitments. Staying local allows tighter feedback loops. Problems can be detected and corrected. Knowledge can accumulate coherently. Evolution tends to favour strategies that balance exploration and exploitation. Too much exploration wastes resources. Too little leads to stagnation. On cosmic scales, the balance may tilt heavily toward exploitation of local environments. Another pattern worth noticing is timescale. Stars live for billions of years. Planets can remain stable for similarly long periods. Life, once established, does not face immediate pressure to move. There is no ticking clock forcing departure. The universe is not rushing anyone. When urgency is low, conservative strategies often win. This may explain why many speculative futures focus inward rather than outward. Dyson structures, artificial habitats, and digital civilizations all emphasize intensification rather than expansion. They concentrate activity around existing energy sources instead of chasing new ones. In such futures, interstellar travel becomes a curiosity rather than a necessity. A project undertaken rarely, if at all, for reasons of pure exploration rather than survival. There is also a cognitive element to consider. Humans evolved as explorers, but that exploration was shaped by environments where movement paid off quickly. Crossing a valley led to new food sources. Sailing across an ocean led to new land within weeks or months. The payoff was tangible and timely. Interstellar exploration does not offer that rhythm. The payoff is delayed beyond individual lifetimes. The feedback is slow. The cost is enormous. Our intuition for exploration may not apply cleanly at this scale. The universe may not be hostile to travel, but it is indifferent to our preferences. Another angle comes from information theory. Communication bandwidth between stars is limited by distance and noise. Coordination across civilizations becomes difficult. Shared projects become impractical. Cultural convergence stalls. Even if travel were possible, sustaining interstellar societies might be harder than creating them. This fragmentation could mean that intelligence in the universe is widespread but isolated. Each pocket develops independently, rarely interacting. The galaxy becomes a mosaic of quiet, self-contained stories rather than a bustling network. From that perspective, the absence of visitors is not surprising. It is expected. This does not require the universe to actively prevent travel. It only requires that the cost-benefit landscape be shaped in a certain way, and when we examine the physics, that shaping seems consistent. The speed limit enforces causality, energy costs enforce conservation, radiation enforces durability, distance enforces patience. Together they form a kind of passive barrier, one that does not say no but asks, is this really worth it? For most civilizations, most of the time, the answer may be no. There is also the possibility that advanced civilizations transition away from physical embodiment altogether. Digital minds, simulated environments and virtual realities change the meaning of place. If experience can be generated locally with arbitrary richness, the incentive to move decreases further. In such contexts, the stars become objects of study rather than destinations. This idea reframes the question. Instead of asking why we have not gone to the stars yet, we You might ask whether going to the stars is actually the dominant trajectory of intelligence at all. The universe offers many ways to grow without expanding spatially. Complexity, depth and diversity can all increase inwardly. Perhaps that is the path most often taken. This does not make interstellar travel impossible. It makes it optional, rare, unnecessary for most outcomes that matter, and rarity can look like impossibility when viewed from a short timeline. There is also a psychological comfort in the idea that the universe keeps us close. It suggests that meaning is local, that home is not a stepping stone but a centre. That exploration does not always mean departure. At the same time, this idea challenges a deeply held narrative. Humans like to imagine themselves as outward-moving, boundary-breaking, destined to spread among the stars. That narrative has motivational power. It frames progress as expansion. But narratives are shaped by context. On Earth, expansion made sense. In the galaxy, the same logic may not apply. The universe may not reward the same strategies at every scale. This realization does not diminish curiosity. It redirects it. Instead of asking how to leave, we ask how to understand. Instead of imagining destinations, we imagine connections through observation, mathematics, and inference. We already see this shift in practice. Telescopes grow more powerful, instruments probe farther, data streams inward, knowledge expands without bodies moving. Perhaps that is the universe's compromise. You may look anywhere, you may know much, but you must stay where you are. If so, interstellar travel is not forbidden, just discouraged. A path with so much friction that only exceptional circumstances would justify it. This brings a certain humility to the discussion. It suggests that our place in the universe is not as a conquering wave, but as attentive observers embedded in one small region of a much larger structure. And yet, the question remains open. Physics does not close the door completely. It leaves it heavy, difficult to open, but not locked. Whether any civilization chooses to push against that door may depend less on technology than on values, on what counts as success, on whether presence matters more than understanding. As this thought settles, attention naturally turns toward a final consideration. If civilizations tend to stay close to their stars, what does that mean for the long-term future of intelligence? Does staying home lead to stagnation, or does it open paths we have not yet imagined? And what does it mean for us here and now as we decide which dreams to nurture and which to let rest quietly among the stars? It is tempting to assume that movement outward is the natural endpoint of intelligence. From early migration across continents to sailing beyond known horizons, human history seems to support the idea that curiosity and survival eventually push societies to expand. But when the scale changes from continents to star systems, that assumption becomes less certain. The universe does not automatically reward outward motion, and in many cases it quietly favours those who stay where they are. A civilization that never leaves its star is not necessarily stagnant, trapped, or incomplete. It may be extraordinarily advanced, complex, and long-lived. It may simply have discovered that nearly everything worth doing can be done locally, without paying the immense costs of interstellar travel. From an energetic perspective alone, a single star offers more potential than most intuitions grasp. The Sun outputs roughly 400 trillion watts of power. Even a small fraction of that energy, harvested efficiently, would dwarf all current human consumption. A civilization capable of building large-scale orbital infrastructure could tap into stellar energy for millions or billions of years, limited more by engineering patience than by supply. With that energy comes freedom of construction. Habitats need not sit on planetary surfaces. They can exist in orbit, optimized for comfort, efficiency, and safety. Gravity can be tuned through rotation. Day-night cycles can be adjusted. Environments can be customized rather than endured. A star system can host not just one world, but millions of living spaces, each with its own conditions. Material resources are similarly abundant. Asteroids contain metals in concentrations far richer than planetary crusts. Comets carry water and volatiles. Gas giants offer vast reserves of hydrogen and helium. With sufficient technology, scarcity becomes a management problem rather than a hard limit. In such a context, the incentive to leave diminishes sharply. Why risk everything crossing interstellar emptiness when your local environment can support expansion, experimentation, and comfort on scales far beyond biological need? Time reinforces this inward focus. Stars live long lives. Even relatively short-lived stars burn for millions or billions of years. A civilization that masters stellar-scale engineering does not face immediate extinction pressure. There is time to refine, to optimize, to explore internally rather than externally. This changes the psychology of progress. When urgency fades, patience grows. Instead of racing outward, attention turns inward. Knowledge deepens. Systems become more intricate. Cultural expression diversifies. Progress becomes about complexity rather than reach. There is also a reliability argument. Staying within a star system allows for tight feedback loops. Communication delays are short. Errors can be corrected. Infrastructure can be maintained. Risks are localized. The difference between a problem and a catastrophe is often the ability to respond quickly, and proximity enables response. Interstellar travel, by contrast, removes that safety net. Mistakes become irreversible. Feedback is delayed by years or centuries. A civilization that values stability may see such risks as unnecessary. This perspective reframes what it means to be advanced. Advancement is not measured by how far you go, but by how well you manage what you have. A civilization that never leaves its star may still possess technologies far beyond anything humanity has imagined. Its quietness would not reflect weakness, but sufficiency. There is also a sociological angle. Large-scale interstellar expansion requires sustained collective agreement across generations. It requires shared purpose maintained despite delayed reward. This is difficult even on Earth, where feedback is immediate and environments change quickly. In a stable, resource-rich star system, the motivation to maintain such long-term outward projects may simply never crystallize. Instead, societies may fragment into diverse cultures within the same system, each pursuing different internal goals. Art, philosophy, science, virtual realities, biological modification, artificial intelligence, and other forms of development could occupy attention indefinitely. Expansion becomes lateral rather than radial. Digital existence amplifies this effect. If minds can be partially or fully instantiated in computational substrates, the need for physical space diminishes further. Experience becomes decoupled from geography. Exploration shifts from physical travel to simulated environments of arbitrary richness. In such a scenario, the stars become data sources rather than destinations. Telescopes grow more sensitive. Probes are sent sparingly, not to colonize but to observe. Knowledge flows inward. Bodies remain local. This does not imply isolation. Communication across interstellar distances remains possible even if slow. Civilizations may exchange information without ever exchanging travelers. Ideas spread where matter does not. Over long time scales, this could produce a galaxy full of intelligent pockets that are aware of each other but rarely interact physically. A quiet galaxy not because it is empty, but because it is content. This idea also offers a potential explanation for the absence of obvious astroengineering signatures beyond star systems. We see stars behaving normally. We see galaxies following expected patterns. There is little evidence of large-scale disruption. If advanced civilizations focus inward, their most significant structures may be subtle, optimized, and hard to detect from afar. They may cloak waste heat efficiently. They may recycle energy locally. They may avoid large-scale expansion not out of fear, but out of preference. From this vantage point, interstellar travel becomes a special case rather than a default. It may be undertaken rarely, perhaps for curiosity, perhaps for survival in extraordinary circumstances, but not as a central pillar of civilization. This challenges a deeply human narrative. Humans evolved under conditions where movement solved problems, when resources dwindled, move, when climates shifted, move, when populations grew, move. That strategy worked because Earth is small and richly connected. The galaxy is not. Movement does not solve scarcity if scarcity does not exist locally. Movement does not guarantee safety if distance amplifies risk. The evolutionary logic of migration may not scale. A civilization that never leaves its star is not static. It is dynamic in different directions. It evolves culturally, technologically, and cognitively without changing address. There is also an ethical dimension. Expansion often involves disruption. On Earth, migration and colonization have frequently displaced existing ecosystems and societies. In space, this might involve altering pristine environments or interfering with potential life. A civilization that chooses restraint may do so deliberately. Restraint does not mean ignorance. It can be a considered response to complexity. This possibility alters how we interpret our own aspirations. Wanting to reach the stars is natural. It reflects curiosity and ambition, but assuming that it is inevitable may say more about our current stage than about ultimate outcomes. We are still young as a technological species. Our local environment feels limited. Our energy use is tiny compared to stellar output. Our lifespans are short. Under these conditions, expansion feels necessary, but necessity changes with capability. A future humanity that can build habitats, manipulate energy, and sustain itself indefinitely within the solar system may feel differently. The stars may remain beautiful, intriguing, and distant without demanding conquest. This does not mean interstellar travel will never happen. It means it may never become routine. It may remain a rare, symbolic act rather than a widespread practice. Understanding this helps resolve a tension. We can admire the stars without feeling compelled to reach them physically. We can explore deeply without travelling far. The universe, in this framing, is not a ladder to be climbed outward, but a landscape to be understood from where we stand. The sense of impossibility shifts. Interstellar travel may not be impossible in a strict sense. It may simply be unnecessary for most civilizations most of the time. When the question of interstellar travel finally quiets down, when engines, energy budgets, biology, and distance stop competing for attention, what remains is something less technical and more personal. Not a calculation, but a reflection. If we never go anywhere beyond our own star in a physical sense, if the stars remain places we study rather than visit, what does that actually mean? At first, the idea can feel disappointing. For generations, the future has been imagined as outward motion. Ships departing, colonies forming, humanity spreading into the galaxy. This narrative is so deeply embedded that questioning it can feel like giving something up, like admitting defeat before the attempt has even been fully made. But that reaction depends on an assumption that movement equals progress and that distance equals achievement. Those assumptions come from a very specific context, one shaped by life on a small planet where movement reliably led to opportunity. When the context changes, the meaning of movement may change with it. If humanity never goes anywhere, it does not mean nothing happens. It means everything happens here. A civilization confined to a single star system is still free to grow in depth, complexity, and understanding. It can build, redesign, and reimagine itself in ways that are limited far more by creativity than by space. The solar system alone contains more room, more material, and more energy than biological intuition comfortably handles. Even now, the vast majority of our system is unused. Planets, moons, asteroids, and orbital space represent a canvas far larger than Earth alone. Remaining local does not mean remaining small. It means working within a region that is already enormous by any reasonable measure. If we never go anywhere, the future becomes less about destinations and more about states. Not where we are, but how we live. Not what we reach, but what we build. This shifts the definition of exploration. Exploration no longer means arriving somewhere new. It means uncovering new structures, new forms of organization, new modes of existence. These can happen inwardly, technologically, socially, and cognitively. Scientific exploration already reflects this. Some of the most profound discoveries of the last century did not require physical travel to distant places. They required new instruments, new theories, and new ways of asking questions. Quantum mechanics, relativity, genetics, and information theory reshaped understanding without anyone leaving Earth. Astronomy itself is an example. We know more about stars billions of light years away than about many regions of our own oceans. Knowledge does not scale with physical presence. It scales with attention and method. If physical travel between stars remains rare or non-existent, observation becomes the primary bridge. Telescopes grow more sensitive. Interferometers span planetary distances. Signals are analysed with increasing precision. The universe becomes more present through data rather than visitation. This is not a lesser connection. It is a different one. There is also a temporal dimension to consider. Interstellar travel is often framed as the future, but futures are not singular. They branch. A future focused on inward development may produce outcomes that outward expansion never could. Long-term stability becomes possible when energy sources are local and predictable. Cultural continuity becomes easier when communication is fast and shared experiences remain synchronized. Ethical frameworks can evolve without the distortion of extreme isolation. Staying close allows problems to be addressed collectively rather than fragmenting across unreachable distances. It allows mistakes to be corrected before they harden into irreversible paths. This matters because intelligence does not just survive by spreading, it survives by maintaining coherence. Too much fragmentation can be as dangerous as stagnation. A civilization scattered across light years, disconnected by time delays, may struggle to act as anything other than a loose collection of historical echoes. If we never go anywhere, we may remain more fully ourselves. There is also a question of responsibility. Expanding outward carries consequences. It risks altering environments we barely understand. It risks imposing our presence on places that may host other forms of life, even if simple. Staying local avoids those ethical uncertainties. A civilization that chooses not to expand physically may be exercising restraint rather than weakness. It may recognize that not every capability needs to be used, and not every frontier needs to be crossed. This idea runs counter to many heroic narratives, but maturity often does. Maturity involves recognizing limits not as insults, but as information. If interstellar travel remains out of reach, it forces honesty. It forces us to confront what we value when distance is no longer a solution. If problems cannot be escaped by leaving, they must be solved where they arise. Climate, inequality, governance, meaning, purpose. These are not problems that disappear with more space. They follow intelligence wherever it goes. Staying home removes the illusion that there is always somewhere else to run. There is a quiet dignity in that. It also reframes legacy. Instead of being remembered for how far we went, we might be remembered for how well we lived, for what we understood, for what we preserved, for what we created that did not depend on conquest or expansion. Art, culture, science, and philosophy do not require interstellar travel to flourish. In fact, they may flourish more deeply when attention is not divided across unreachable horizons. There is another possibility worth sitting with. If no one goes anywhere, then perhaps no one ever has. Perhaps the galaxy is full of civilizations that stay near their stars, learning, adapting, and fading without ever touching one another physically. If that is true, then the universe is not empty. It is simply quiet in a particular way. Quiet does not mean lonely. It means separate. It means that each pocket of intelligence experiences the cosmos from its own vantage point, building meaning locally rather than globally. In such a universe, significance is not measured by expansion, but by richness. A civilization's success is not how widely it spreads, but how deeply it understands and shapes its environment. This idea can feel unsettling because it removes a familiar ladder. There is no inevitable march outward, no guaranteed galactic presence, no final image of humanity among the stars. Instead, there is continuity, long-term stewardship, iteration, refinement. That may be harder to dramatize, but it may be closer to how the universe actually works. It is also worth noting that not going anywhere does not lock the future permanently. Physics does not declare an eternal ban. It simply sets cost high enough that choices matter. A civilization may choose to remain local for thousands or millions of years, and then change its mind under different circumstances. Staying home now does not mean staying home forever. It means not assuming that leaving is the default or the goal. If interstellar travel turns out to be impossible, or so impractical that it never happens, the universe does not become smaller. It becomes more intimate. Attention turns inward. Responsibility increases. Meaning becomes something that must be cultivated rather than discovered elsewhere. This can be uncomfortable. It removes the fantasy that salvation lies somewhere beyond the horizon. It insists that value must be created, not found. But there is also relief in that insistence. It frees us from measuring worth by distance. It allows curiosity without restlessness, wonder without entitlement. The stars remain. They do not vanish if we cannot reach them. They continue to burn, to change, to teach us through light and time. We can know them without touching them. Perhaps that is enough. And perhaps the final measure of a civilization is not whether it escapes its birthplace, but whether it learns to live fully within it, aware of the vastness beyond, humbled by it, inspired by it, and content to listen, to observe, and to think, while the universe continues quietly doing what it has always done, whether anyone travels through it or not.